and applications. My name is Lucia Giannuzzi. Welcome. I see that a couple of people that have signed on still have not muted either their phones or computers, so can you please do that? This will prevent feedback. No audio. Let's see. Okay, so I am not muted. So have you, can someone, can anybody hear me? Are you guys hearing me?
Yes.
Okay, yes. So Dana, can you, can someone write
Dana,
yeah, Dana is not able to hear us, so I don't know if she's signed in.
Dana, are you connected via your computer, or are you calling in? I can't hear her. Okay, let's see.
Let me just give me a second. So I'm not able to send messages for some reason. Okay. So everybody turn up the sound if you can. My microphone is completely turned up. Okay. All right. So it should be a little bit better. So again, please just mute your speakers so that you don't get feedback. So to ask a question, that seems to be working. Just enter it in the Q&A or the chat box and send it to all panelists. And I have a second screen, so I should be able to see them hopefully before too many slides go by. If you have questions, please, it's okay to ask on the fly. If not, I'll try to get them at the end of the lecture. There'll be 3 approximately 10-minute breaks. We'll see how things go in between each of the lectures. And again, I'll either hit the questions at the end of the lectures, or again, if you have questions during, please don't hesitate to ask me questions via the chat box, and I'll try to get it now. And just some other things coming up, the AVS short course program at AVS 65 in Long Beach, California is coming up next month in October. Check out the AVS short course schedule page for course schedule, and let's see. Okay, and some other upcoming events. There's technical meetings sponsored by AVS, in addition to AVS International coming up, as well as the short courses. So please feel free to take a look at that. Okay, so let's get started. So you're here for Focused Ion Beam to learn a little bit more about FIB. I'm going to talk about an introduction to FIBs and mainly now FIB-SEM instruments, dual platform instruments. We're going to talk about hardware, ion-solid interactions, imaging, and contrast theory. So again, we'll just head right into it. There's a lot of reference material. Some of my colleagues refer to this Intro to Focused Ion Beam book as the hot pink book. I defer and disagree. It's the magenta book, but that's an inside joke. Oops, let me go back there. Sorry. There's also there's work involved to updating this book, but that's probably about a year or so out. The MRS bulletin talks about focused ion beam, microscopy, micromachining. These two MRS bulletin were specific issues on FIB, both for applications as well as nanoprototyping. There's other references. The one by Orloff, Utlad, and Swanson has applications, really good also for learning more about FIB instrumentation. The Charged Particle Optics book by John Orloff, again, is another book to learn more about the makings of a FIB column. Focus ion beam systems, again, is some more references in there. Okay, so there's a whole bunch of references out there. Let's talk about some of the instruments. People always ask me, what instrument should I buy? And the question I always push back on them is, what are you trying to do? There's not one vendor that does every FIB application perfectly. And there's a reason for that, mainly because there's different detectors, there's different geometries, and the more things that you want to do on more instruments, the more difficult it becomes to do everything exactly perfectly the way you want to. So there are better instruments for TEM sample prep, for 3D analysis, for nanoprototyping, etc. And again, the more things that you want to do on the instrument, the harder it becomes. There are different geometries. There are gallium FIB columns. There are xenon plasma FIB columns. There are triple beam systems that have argon beams on them. Different types of SEM columns. The Zeiss Orion NanoFab has 3 different ions on it as well. So there's a lot out there. Mainly what I'm going to talk to you about today can be done pretty much on any instrument with specific exceptions that I'll talk about, for example, specific ions that may be available only on particular types of columns. But when we talk about basics of sample prep and things of that nature, most of these instruments can do it all. Okay, so let's talk about first the advantages to FIB in general, or particularly FIB-SEM or FIB columns, is that basically techniques that were not possible with an individual FIB column by itself became feasible with the addition of an SEM column or a second column, basically in general, whether that be a FIB or an SEM. Particularly TEM specimen preparation, for example, became easier because you can see or endpoint with the SEM. The addition of the SEM enables 3D materials characterization more easily, where you can look at microstructure, crystallography, and elemental analysis using the electron beam as a signal to collect either for imaging, for EBSD or EBS, for example. You can also combine E-beam machining and prototyping with ion beam machining and prototyping. There's all sorts of in-situ analysis that's available as well, cold stages, hot stages, straining stages, etc. Note also that different vendors have geometries slightly different. Some FIBs are vertical and the SEMs are tilted with respect to the FIB. Most of the instruments have the FIB vertical with the SEM vertical with the FIB at some tilt, and there are some FIBs that are also perpendicular to, for example, an SEM. So there's a lot of different varieties and flavors, and there are also some FIB columns, FIB instruments out there as well. Again, it really depends on what you want to do and how you want to do it. Okay, so the early use of FIBs really started with mass repair and device or circuit modification. This gradually led to the ability to just cut through things and look at them. So basic 2D imaging, and then combining slice image, slice image, slice image for 3D imaging. And then, of course, because you can site-specifically remove material, this developed into the ability to do micro and nano site-specific milling, because you can do ion beam-assisted chemical vapor deposition as well as electron beam chemical vapor deposition, of course, You can do micro and nano site-specific deposition. And then basic specimen preparation, well, whether it be 2D specimen preparation, for example, for just FEM analysis. One of the big applications is for TEM, but what I'll show you also is that you can take these site-specific samples and take them to other types of instruments, such as surface science instruments, atom probe analysis is big, EVSD, et cetera, et cetera. And then the computer automation of all of the above has just enabled us, again, to do things that were just impossibly long to do and or just difficult because we weren't able to automate processes. Okay, so over the years, basically, if you can think of it, it's been FIB mills, any kind of material now. I haven't come across anything that I haven't been able to FIB mill. Semiconductor, metals, polymers, ceramics, composites, biological, geological, pharmaceutical, et cetera. And then in all different shapes and sizes, cross-sections, plan views, false monolithic, fibrous particles, difficult shapes, thin films, et cetera. If you can get it into the instrument, you can start FIB milling on it. All right, so let's talk about the basic column itself. The basic FIB system basically consists of the source, and the source is going to depend on what sort of ions that we're getting as well as what resolution of ions we can get. The column, detector, the vacuum system, gas delivery types of systems, different stages, probes, sample itself, charge neutralizer, what kind of setup you've got, whether it's FIB-SEM, FIB, and then what kind of other detectors are on the instrument, and of course all computer control. So first we'll start with the source and focusing optics, anywhere from a few hundred eV to 50 kV. A lot of instruments use 30 kV is sort of a magic number. 2 electrostatic lenses or more. And again, electrostatic lenses are used instead of electromagnetic lenses because the ions are heavier than electrons, and you need electromagnetic lenses, which are much larger to be able to handle and focus these heavier ions. You've got a deflection electronics or patterning board engine. This scans the beam, rasters the beam where you want to, patterns it in different ways. High-speed blanking is sort of the standard for FIBs because you want very fast site-specific placement of the beam, whereas that's usually an option for an SEM because SEM is mainly just used for imaging. So a lot of times if you want to combine, for example, nanoprototyping of the ion beam as well as the electron beam, you have to make sure that your SEM has a high-speed blanker as well. Ion getter pumps, these are usually 2 pumps to reduce particle interactions with the beam, and columns are generally compact to simplify construction and minimize coulomb interactions. All right, so you should become familiar with this, particularly with a lot of different ions that are out there now and different types of FIB instruments. You'll see a lot of people reference this sort of graph in the literature. This is in the MRS bulletin and was given to us by Noel Smith at Oregon Physics. But basically, this is the beam diameter or size of the beam as a function of beam parent. What you see basically is that different types of ion sources generally yield or lend itself well to producing different types of ions, which also lends itself to very different behavior and types of things that you can do. So at the very high end, if we take a look at this log-log scale, you see that we can achieve pretty high currents, but very large beam diameters, and this is sort of an argon electron impact source. type of a FIB, if you will. So these are the type of instruments that you might see, or the type of sources that you might see in like an ion polisher, which is typically used now to just cross-section lots of, or just cross-section huge amounts of material very quickly. Some of these don't have a focus beam per se. They're just a very large opening in a beam opening, and some do scan the beam, but mostly you're just talking about opening up the beam or allowing the beam to come through a very large aperture that hits everything in its line of sight. Okay, on the very low end here, this is basically your gas field ionization sources. This is your helium neon sources. This graph here just shows helium. And what you see is that these currents available, which are available, tend to be extremely low. The beam diameter tends to be extremely small, which also means the resolution is really sub-nanometer, and in some cases sub-angstrom. So these are going to be good for imaging as well as really good for nano-patterning. And then the ones in between, the one in green, this is your gallium liquid metal ion source, which most people are familiar with. And then the one above it is the plasma FIB, which typically we use xenon for most FIB applications, but you can use other reactive ions, for example, for SEM. So let's take a look at what happens between these two sources, because these are the ones that are used most often, and even the deepest source. Most people are familiar with this gallium gas field ionization source, and a lot of FIBs have high beam currents available up to about 100 nanoamps. But what happens above about the 10 nanoamp range is that when you start with a small virtual source and you have to get more current out of it, the angles increase dramatically. This yields to spherical aberration. We'll talk a little bit more about that later. And what this means is that as you keep turning up the current, now you don't get this linear log-log relationship basically for these large beam currents. And the beam diameter gets very, very large as you turn up the beam current. You can still operate a gallium FIB at about 100 nanoamps, but the beam is really, really large, on the order of about a micron or so. Compare this with a xenon plasma FIB source, and what happens is that since the virtual source is starting out much bigger than a gas field ionization source, you can turn up the current of this source to the microamps region and keep this linear log-log scale. What this means is that above about 10 nanoamps, the xenon plasma FIB becomes much more efficient at milling large features versus the gallium the gallium liquid metal ion source FIB. And so that's where you're seeing a lot of the plasma FIBs come in now, is that they're milling larger features more quickly than the gallium gas field ionization source. And you can see at the low end here, there's a difference of about an order of magnitude between the resolution, although the improvements in the plasma FIB is coming down such that these numbers here are getting lower and lower. Okay. So let me just go back again one more time. So the point that's really cool about what's going on in FIB now is that you've got multiple different types of instruments that can hit a large range of length scales, from literally the nano scale or even sub-nanometer in some cases, all the way up to the micrometer or millimeter range of trying to either cross-section or pattern material. Okay, so depending upon what type of source that you use will also, in some cases, dictate what sort of ion is available. In some cases, the ions are available in multiple sources. But you see here the ones in sort of this salmon color is the liquid metal ion source or the liquid metal alloy ion source, and I'll tell you more about that later. There's also a source being developed now called the low temperature ion source. Currently this is available in lithium and cesium. This is another very good resolution source that's available. You have the gas field ionization source, helium and neon, and then you have this plasma source, which is xenon, argon. It can also be neon, and it can also be some other gases like oxygen, for example. Okay. So again, there's your different sources, your liquid metal ion source, your liquid metal alloy ion source, gas field ionization source, plasma FIB source, and a low temperature ion source. And for a review of sources, you can see these MRS bulletins from 2014. So we're going to talk a little bit about these sources. So the liquid metal ion source has pretty much been the standard over the past 2 decades or so. Basic operation of how this works is this is the source itself. Basically, you have a tungsten tip, and the tungsten tip sits on this coil for a reservoir, which is also conductive. You've got these conductive wires that lead to paraconductive wires with this ceramic non-conducting material. So this sits in there, basically flows current through one way into the other. The current heats up gallium, which sits in this little reservoir. So gallium is nearly liquid at room temperature, so you don't need to turn up this this current very high in order to turn this solid gallium into a liquid. What's the scale of the tip of the image? Someone says this is the tip is on the order of about a few microns, I believe, maybe even smaller. But that I actually have one next door, so at the break I'll actually get it and show it to you in my hand. So that's about a millimeter-ish, I think, something like that. So the entire source is only about that big. I'll show it to you later. Yeah, so what happens is a little blob of gallium just flows down the tip, or the liquid metal flows down the tip, and you want it with a little tiny blob of gallium. And then what you do is you throw a high voltage across there, and that generates a so-called Taylor cone. The Taylor cone becomes unstable, or excuse me, the Taylor cone stabilizes, but then you get ions from it, and I'll show you a little bit more about that too. And because gallium can remain superheated, you tend to you don't have to keep it heated. You heat it once, and it will stay working as long as you're using the gallium until this little blob is depleted. So it can work for a week or more before you have to heat it again. Oh, I guess I don't have a picture of that. Oh, let's see, do I? Oh, maybe not. So anyway, let me go back a sec. So people always ask why gallium, and basically it's because the gallium works really well in this type of source. It's nearly liquid at room temperature, so it's really easy to control. As I said, you only have to heat it once and then use it for hours and hours and hours before you have to heat it again. Its emission characteristics are really good. It gives you really high angular intensity and low energy spread, which reduces the aberrations, long life, high vacuum compatibility, and it's a heavy ion that for sputtering. So basically it gives you the best of all worlds, and it's most easiest to use in a commercial instrument. So why might we use other ions, however? Gallium, first of all, can be, well, let me start over. Gallium can be detrimental or can yield detrimental results to certain materials. First of all, it's a dopant in silicon and some other materials. It segregates to aluminum alloys. You can actually get gallium droplet precipitation in gallium-based intermetallics due to difference in milling rates. And in some cases, you might want to just generate different ion-solid interactions. That is, get different types of sputtering behavior, different kind of secondary ion emission, for example, through doing SIMS analysis, etc. So if we take a look at, this is a shrimp calculation. These are Monte Carlo calculations showing ion trajectories and the recoil interactions. You can see that we've got helium, neon, argon, gallium, and xenon. And as we go to heavier and heavier ions, this is all in silicon at 30 keV, you can see that the heavier ions are stuck closer to the surface, and this is all at normal incidence. So the ions are coming in perpendicular to the sample surface. Helium has a very small spread at the surface, but then travels microns length into a sample. Whereas these other ions that exhibit so-called sputtering and heavy ion effects will be stopped only a few tens of nanometers within the surface. So it really depends on what you want to do, how you want to do it, what effects you want to get for either sputtering or to minimize damage, etc., which we'll talk about. Okay, you can also use liquid metal alloy ion sources to get different types of ions. And the way this works is basically you're using a eutectic alloy. So you're using a mixture of two or more materials in the liquid metal ion source. And then you use a filter, an E-cross-B vein filter, to separate out which ions that you want or you need. So here's an example, and this is why you use a eutectic alloy. So this is a gold-silver phase diagram. So this is gold, this is silver. So what these lines show you are the melting points for each of these elements individually. So the gold is up here close to 1100 degrees C. The silicon is way up here, close to about 1400 degrees C. So that would be a real pain in the neck to try to heat those up. So if we combine the two and use the composition of 18.6 atomic percent silicon, we can lower the melting point of this mixture to only about 363 degrees C. So we can operate then this mixture of this composition at a much lower temperature than we would either gold by itself or silicon by itself. Okay? What this means, however, is that we've only got now in here, we've got a lot less material to work with, and so liquid metal ion sources, liquid metal alloy ion sources tend to have reduced amount of current that's available versus a liquid metal ion source, because if you pull, for example, 2 microamps out of the source, but you've got less material here that's available, you're only going to get a lot less, for example, a lot less, in this case, gold that would be available even using these same apertures. Okay, so here you've got your probe current selection apertures. You would have the ion beam come through, and then you have to have this filter to filter out which ions that you want to use, whether it's the gold or the silicon, and then you've got your mass selection apertures after you separate this out by mass. Okay. And there are commercial instruments that are available that do sell liquid metal ion source, alloy ion source instruments. Okay, so this is what a typical column looks like. You've got your source, you've got your suppressor and extractor, there's a spray aperture or beam emitting aperture, then you've got your lenses, octopolls for scanning, And then you've got your variable apertures which adjust the current. And then you've got your beam deflectors, lower octopoles, and second lenses for focusing. And then you can have different sorts of detectors, perhaps right under the column or elsewhere in the chamber on your sample. Okay. So it's also possible, as I mentioned, to use a liquid metal ion source, liquid metal alloy ion source. Sorry. So here, for example, we can use silicon plus plus, or we can use gold plus plus, or gold 2 plus. And because these masses differ, this also corresponds to a different amount of sputter yield, where the sputter yield is atoms per ion. Okay, but perfectly possible to do that. So you might want to, for example, use a particular source if you're looking at different materials. Okay. All right, the plasma source is basically, it has no cathode. It uses an external radio frequency antenna, which couples energy to the plasma electrons inductively. This yields a very long life, high purity beam from inert and reactive gas species. So if you've got, typically, actually, xenon is pretty expensive. It comes in bottles that are only about this big, but if you have a bottle of xenon that's about this big, it will last you your lifetime and probably the lifetime of your children and grandchildren. So you don't need a lot of gas at all for this source. So, so that's a good thing. However, because you're typically using this at much higher beam currents, you're going to use consumables such as apertures and other things that are going to wear pretty quickly. Again, automated gas delivery. Again, infinite source in the sense that if you have a gas source container, small little bottle about this big, you will be able to use it for the entire life of the instrument. And it's a very high brightness source, which again allows us to mill things that are much larger with much smaller beams. So the current density at the high end is very good. And again, this is a similar graph to what I showed before. Probe size is a function of probe current. This is your gallium. This is your gallium up here, where you see at the knee here. This extends upward because of spherical aberration issues. And at the high end, the xenon plasma FIB just continues to extend linearly on this log-log plot, so you get really, really good probe size, probe current behavior, allowing you to mill very large things very effectively. Okay, so just to compare the two, at 100 nanoamps, the xenon plasma FIB gives about a 1 micron beam. Gallium with a metal source gives about 10 microns. So what this means is that you've got 100 times larger milling rates on the xenon plasma FIB versus the gallium FIB. And this is, you get sort of like a 2-for-1 punch here. One is that you can go to higher milling rates with the xenon plasma FIB, and two, because the xenon is heavier than gallium, you also get a blast additional factor of higher sputtering due to that as well. Okay, so two effects there: the larger beam current that's available, as well as the larger mass that's available by going to xenon. All right, so this shows how just the difference in speed. So again, people would always ask me, well, what's the largest size that I can cut with a gallium FIB? And my answer was, how long do you have? So basically, if you've got an infinite amount of time, you can cut through stuff with a gallium FIB. But then, in many cases, time is money, and so you're just kind of spinning your wheels in some cases. So this is an example from, again, Noel Smith at Oregon Physics. This is an IC pad. Ball bond, 750 microns. Gallium FIB milling, 6 hours of gallium milling with 50 nanoamps. And basically, barely kind of tickled the surface. Okay, so this would require another 250 hours to complete. If you take a commercial rate of $400 per hour, that's $100,000 just to cut through this ball bond using gallium fib. Compared to using a xenon plasma fib, you can do this in about 6 hours with first 2 microamps, then 100 nanoamp polish, followed by 100 picoamp image, all within 6 hours. And obviously, there's a great cost reduction just in instrument time itself. Okay, so again, there's the big advantage to being able to use the xenon plasma fib for larger fib milled regions. So really, your realistic limit in a gallium fib is going to be probably 100 microns at the upper level. Really, 50 microns is probably more reasonable. Anything larger than about 50 microns is really not a gallium fib job, unless it's the only thing that you have and you're willing to sit there long enough to mill through very large materials. So here's some example by the work of Burnett et al. A couple years ago, and they were looking at material doing 3D analysis, basically in the same amount of time here. This is a xenon plasma fib versus gallium fib for 3D analysis, and in the same amount of time, they looked at, I don't know what the factor is here in volume, but maybe 1, 2, 3, 4, 5, 6, at least 10 times more or more. So again, you can just fib through larger materials faster using xenon plasma fib. Okay. All right. And yes, you can make TEM samples with the plasma fib. So people would always ask me, can you make a TEM sample? You know, this was a few years ago. Can you make a TEM sample with plasma fib? And the resolution, the first kind of numbers that were being thrown out there were sub 50 nanometers. I'm going to show you examples when we talk about TEM sample prep. The initial techniques were developed in the mid to late 90s using a glass column gallium liquid metal ion source fib with a resolution of 50 nanometers. The plasma fib came out and it was already better than that. So of course you're going to be able to make TEM samples using the plasma fib. The xenon, of course, gives you some added benefits. One is that because it's heavier, you get reduced sidewall damage. And 2, you can just do larger things. So this is some work that I did with Joe Michael and his group at Sandia, showing lift out of a meteorite sample, put it on these special grids, which I'll tell you about later. EVSD off of the surface. And this was, I think, finished with 10 kV xenon. And then back into the plasma fib for additional thinning for STEM and EVS work. So yeah, you can do this. This fib, plasma fib specimen was about 150 microns by about 40 microns, so not a problem. Okay, I'll give you some other examples. Okay, gas field ionization source. This is a unique source because this uses technology that's similar to how atom probes work. So basically what you're doing is you're getting a tip, you're sharpening a tip to a very short point, and you're putting a high field on this tip in the presence of helium. And what you wind up doing is getting these small little beamlets of helium sources. And the idea then is you sharpen the tip to where you get sort of this primer at the source. What's not shown out here is that you do get some smaller emission from back around here, but that's not critical. The idea is that you get this primer of sources. So these 3 atoms which are sticking out from the tip is basically your source of helium ions. And then what you do is you just tilt the source such that just one of these beamlets come down the column, okay? And then after this ion gets, or this atom gets popped off or gets degraded, you can then tilt in another one of these and the third one, for example. So because you're starting with such an extremely small source to begin with, literally from just a single atom, this beam produces extremely low or extremely high resolution, I should say, ion source. But again, because you're only getting ions generated from a single atom, the sources tend to operate at much lower beam currents that you would be used to from, for example, gallium or xenon positive. Okay, but once you generate these ions from a single atom, the rest of the column is pretty much the same. It pretty much looks exactly like another thread. So you've got your extractor, your focusing optics, your aperture, your span coils, etc. Okay. As I said, though, because the total emission by the entire timer is only about 100 picoamps, and you only are putting one of those through there, only about 5 picoamps from one emission site is available. So the highest resolution is achieved with only about half a picoamp. Smallest probe, again, is sub-angstrom, is about sub-nanometer, 0.35 nanometers for helium, and 1.9 sub-2 nanometers for neon. So really for extremely high resolution nanometer scale size work. The advantage to the helium ion microscope, contrast mechanisms, and actually ion beams in general, is you do get the conventional ion contrast, voltage contrast. You get your conventional material contrast. You get the large depth of focus, and this is, again, generic to most ion imaging. Ion imaging, again, in general, is extremely surface sensitive, but with the helium ion microscope and the very small probes, this limits sputtering. And ion imaging is really a pure secondary electron signal. You can also get Rutherford backscattering, ion imaging, and some other types of imaging. So it's really good for imaging. And again, if you're just talking about drilling holes, it's really good for drilling holes in freestanding membranes where you don't get the build of helium deep within your sample. So if you have freestanding membranes, you can make extremely small holes. And this is just a comparison between a gallium fib and a helium ion microscope, and you can see the extremely small holes that are available down to about 5 nanometers, whereas using a gallium fib on the same material, you're limited to about 50 nanometers. Okay. And just for your information, again, there is something called a low temperature ion source. This uses laser cooling for photon or photoionization. Again, cesium ions and lithium ions are also being used. Other alkalis or noble gases and some metals are possible. Basically, it has to be the ions or the material has to be able to be photoionized. There's just some development going on with that, but no commercial instruments that I know of that are currently available using this source. Okay, so we talked a lot about imaging. We talked a little bit about masses and how this affects sputtering, but now we're going to really get into the ion-solid interactions and talk about how this all works and why this works. So you have an incoming incident primary ion. And again, this can be gallium, neon, helium, whatever it is. This is going to come in and get bounced around just do similar to a cue ball hitting a bunch of billiard balls, okay? So this is going to generate, particularly for heavy ions, what's called the collision cascade or the recoils. So these moving atoms inside of the solid are the recoil atoms. This generally results in an implanted ion. This can also result in internal defects in the material. So it can result in interstitial atoms or vacancies or other point defects. At the extreme, it will also cause a metastable amorphous phase, and we'll talk more about that later. The other thing that you will also get at the surface are the generation of the secondary electrons. These are caused directly by the incoming incident primary ion as well as the energy of the moving recoils. You'll get sputtered species. You can also get X-rays or Auger electrons, but these signals are very, very low. And then you can also get secondary ions, and these secondary ions can be used for imaging or also for secondary ion mass spectroscopy or spectrometry. Excuse me. You can also get, of course, neutral ions. So basically, we can control then, if you think about it, we can control which types of species we get by controlling the ion type, the ion mass, the ion energy, and also the ion incident angle. And what also affects what's going on here, of course, is the solid that we use, the target. And what we don't see here is that the target crystallinity can also affect what's going on with the ion-solid interaction. So again, first, if we just talk about angular scattering cross-section, given by this equation here, we see again incoming ion M1 can hit your target. This makes the target move off one direction, and the ion can be pushed into another direction. Associated with this is an energy loss. This cross-section here is basically just a measure of the probability of an event. Okay, so if we're just concerned with the angle that an ion scatters, we see the scattering cross-section as a function of angle. We see that the probability of this being scattered at 180 degrees is pretty small compared to the angle of scatter at 2 degrees, which is a lot bigger. So what this means is that most ions are scattered at very, very small angles, okay? They're not going to come back basically at you. There's about a 7 orders of magnitude difference. And you can see that here. Most ions, there's the ion trajectories. They're basically coming in at the similar ion. In this case, it's 0 degrees. In this case, it's 89 degrees. They're going to stay basically very, very close to what their initial path into the solid is. Okay, so most scattering events are very low angle, and deflections are mainly due to the interactions of the ion with the nucleus of the target ion. Okay. Excuse me. Okay, so we also have to know about energy loss, stopping power, and ion range. Now, of course, if you've got this incoming ion and it's going to smack into some other target atom, it's going to lose some energy. So not only is it moving at some different angle, but when it does so, it's going to lose some energy just due to change of transfer of momentum, okay? So then the total energy loss is a function of elastic and inelastic scattering. Okay, so your elastic scattering is due to is the nuclear stopping power, and your inelastic scattering is your nuclear, and I just went brain dead. Sorry. There's other inelastic scattering power, and I just totally forgot what that E is for. So it'll come to me. I apologize. The point is that most of your heavy ions will be scattered due to this nuclear scattering, except for the very light ion such as helium, which will be, I'll show you, suffers from mostly inelastic scattering. Electronic, thank you. Phew. All right, I got it. Electronic scattering. So we can then take this energy loss per unit length and determine what our range of the ions are going to be, okay? And we can also determine which part of this effect is nuclear stopping power. Here's my electronic stopping right there. There's my electronic. So we can determine what the range is if we just substitute in the masses and the atomic numbers of the target and incoming ion respectively, okay? And this is good for the typical accelerating voltages that are used in FIB. So again, if we consider that we're throwing an ion at a cue ball at a bunch of billiard balls, or similarly if we're taking a bowling ball and throwing it at a bunch of pins, if we take helium, which if you think of helium as a little tiny pea trying to hit into these very, very heavy bowling pins, you're going to see that the interaction, the nuclear interaction, is extremely small across the periodic table, but the electronic stopping is really large. And conversely, if we go to a heavier ion such as gallium, we see across the periodic table that the nuclear stopping is very large, the electronic is smaller. And as we go to a larger mass ion such as helium, or excuse me, xenon, we see that the nuclear stopping is even larger than gallium, and the electronic stopping is smaller than gallium. Okay? So you can see this inverse effect as we go from a very light ion to a much heavier ion and even a much heavier ion. Okay? So we can think of this bowling ball here as either gallium or xenon, where the harder that you throw it, the more these pins are going to get tossed around. And as we come in then with a bowling ball that's going very slow, we can see that we won't get very much interaction of these pins. Okay, so that's what we're going to use to actually site-specifically remove material. So the FIB then is we're going to use this to, again, site-specifically remove material. So we're going to use our little site-specific backhoe, if you will. We're going to use, again, the interactions of, if you play pool, a white cue ball with a billiard ball, or if you're used to bowling, or lawn bowling, or bocce, or curling, whatever your sport is, you can think of it. We're going to introduce one heavy ion, for example, and we're going to blast away and start removing, site-specifically remove ions. And the way we do that is with physical sputtering. So let me show you a movie. This is from Barbara Garrison at Penn State. This is 15 kV gallium in gold. You can go to our website and see a whole bunch of these different movies. So there's the side view. The one thing you note is that this is just one single ion, and you can see hundreds, literally hundreds of recoils that are generated. This is the top view. So it's coming in at an angle, so you can see that everything is sort of coming in about here, so everything is pushed this way. And let me play this again for you, because I want you to concentrate on a blue particle or blue atom that's going to come in, going to come out right about here. There. You see that go off there? So the one thing that you notice is that right away is that where the incoming ion entered the sample surface and where the outgoing recoiled atom moved from the surface were two different dimensions. So people would always ask me, well, I've got this 2 nanometer resolution ion beam. Why can't I mill a hole that's 2 nanometers wide? And this is the reason. One is because the recoils come from a distance that can be several nanometers away from the incoming ion. And two, then of course, with that same 2 nanometer beam in different materials, just because the ion-solid interactions are going to be different, you're going to have, you're not going to be able to mill the same type of hole in different materials. Okay, so the sputter yield then is this mean number of ejected atoms per incident ion. So we've got the nuclear stopping, the surface binding energy, the N is the atomic density, and alpha is the function of mass ratio between the two. It's just given, again, by this function, where the energy loss, again, is really important. So basically, as the stopping power or energy loss increases, the sputter yield increases. And just note that this surface binding energy is really difficult to measure and is a big influence by surface conditions. So if we take a look at sputter yield now, and how different things sputter, there's a lot going on here. So let's start off by this upper right area here, which I showed you previously. This showed that, of course, you're going to get very different ion-solid interactions for different ions in the same material, same energy. Okay, we look at sputter yield versus incident angle. For 2 different materials, we see, first of all, that the sputter yield of copper in for gallium and copper is about 2.5 times larger than, or 3 times larger than for that in silicon and gallium and silicon at 30 kV. It reaches a peak, and we see that we get very, very fast milling at the surface. And so what we're going to try to do when we do specimen preparation is always good mill on the surface, because this is going to generate our fastest milling. Look at also the sputter yield as a function of ion energy. And we see that as we go lower and lower in energy, the sputter yield basically goes to 0 and can actually go below 0 in some cases. Are the dips in the copper yield due to channeling? No, this is not due to channeling. These little dips are just probably due to poor statistics. Generally, if you want to do these shrink calculations, you should do 10,000 ions or more. So this would probably be a lot smoother if the number of ions used in the shrink calculations were a lot bigger. I'm not sure exactly how many were used here, but that's probably the effect that you're seeing. Let's see. Okay, the range. Here's the range in ion energy. So we see that for all ions except for maybe helium, well, for all ions, let's say, as we lower the energy, the range decreases. Okay, period. So we're going to use this fact. The fact that we know this, and the fact that we know this, that the range decreases a function of ion energy, and we're going to apply this to our low energy polishing so that we can make really pristine surfaces for improved EBS and sample prep, particularly for TEM sample prep. And we also see that the range decreases as a function of incident angle. But what we also notice is that we go to low energy, this effective incident angle on the range is not affected by energy. Let me start over, sorry. We take a look at range versus incident angle. At 30 kV, we see a huge difference. Okay, so the range is going to vary dramatically at 30 kV. When we change incident angle, and that we can just see here, right? So the range is changing drastically, or the sputter yield changes drastically, and so you can expect that the range changes drastically. As we go to lower energy, the effect of incident angle on range decreases. So this means when we go to our low energy polishing considerations or low energy polishing routines, we can get away with hitting our surfaces at greater angles and not have to worry about increasing the damage very much. So also, if we take a look at this bottom left curve and match that sort of with our sputter yield curve, we see that as the angle of incidence changes on a particular asperity or pillar, we're going to get different angles of incidences, and therefore we get different sputter yields. So this works out perfectly, for example, for making atom probe tips. You can take advantage of this, again, by cutting on an angle. This is also why, however, if you've got a big chunk of material in your sample surface, it's really hard to get rid of it because the sides are going to mill faster than the top, and you're just going to wind up building pillars. And so it's really hard to get rid of, actually, pieces of things that are sticking up higher than others. All right, so let's try to move along a little bit more. Back sputtering, this is important to know because this will tell you if you've got redeposited material, particularly on your TEM sample. If you hit your material normal to your incident, normal to the incident angle, sputtering will come off in this cosine distribution, and the back sputtering will increase, or the amount of material that you come off, or the amount of gallium, for example, coming in, will be forward sputtered, and this will increase up to almost 90 or 80, 75% of the incoming gallium will be back sputtered at these high incident angles, whereas at normal incidence, almost zero gallium will be back sputtered, or basically almost zero, let me say this differently. Almost 100% of gallium, or xenon for that matter, coming into a sample normal to the surface will be implanted. But the sputter particles coming out will come out in a cosine distribution. Conversely, if you're on an angled surface, almost 75% of the incoming ion will also come out. This is what this shows. So this is a really good indicator. If you see a high amount of gallium in your TEM samples, for example, then this is due to redeposition effects and not due to the basic ion tolerant interactions, and I'll show you some of that later as well. This redeposition is also attributed to V-shaping, both in milling trenches as well as milling TEM samples. So, for example, if you're trying to mill a feature mill a hole into a feature, this hole will always result in this V-shaping. And the amount of V-shaping is going to depend on what kind of beam current that you're using and what kind of material that you're cutting into. And if you're making a TEM sample, this will result in sort of an opposite V, where the sample's thicker at the bottom and then it is at the top. And this is why we always, in some cases, tilt into our sample. When we're making TEM samples, we'll tilt into it plus or minus 1 degree or 2 degrees. That angle will vary depending upon what we're signaling. Okay? And as I mentioned before, the amount of redeposition that you see is really a function of how much gallium that you can collect or determine into your sample. So this is looking at sidewall damage in silicon. And in this sidewall damage, you see the typical amorphous layer, which is noted by 3, and then you see this other darker layer denoted by 4. And if you use the EDS of that in 4, you're seeing almost 48% gallium. This is a redeposition artifact, which is where in 3 here, that's your typical amorphization layer. So if you're seeing, again, a lot of a lot of gallium in your samples, that's a redeposition artifact, and that's not an ion-solid interaction, inherent ion-solid interaction artifact. Okay, so when you ion implant, again, I mentioned earlier, you can also generate a metastable phase. So ion bombardment can disrupt the lattice in a way that causes, quote, local melting. And notice this is in quotes, okay, because you're not going to melt a sample. Excuse me, let me go back. So people always ask, what kind of temperature rise am I going to get in my material? And basically, the temperature rise inside of an inorganic material is basically insignificant. Everything is happening at the surface, the top few tens of nanometers. And this happens extremely quickly within just a few tens of picoseconds. So when all these atoms are jumbled up, like you saw in the video I showed earlier, this can be considered liquid-like in the sense that there is no structure here. There is no long-term order or any short-term order for that matter, okay? But what happens is that these atoms immediately start to relax. And whether or not, when they relax, they can find their equilibrium lattice positions will determine whether or not you form an amorphous layer or not, okay? So again, this all happens extremely quickly. So if we take a look at 10 kV gold on gold, we see no amorphization. What we see here is that we've got some crystalline defects, some interstitials, some vacancies, et cetera, a little bit of swelling, but no crystalline defects. Excuse me, no amorphous phase. So the amorphous phase will form if these atoms cannot find their equilibrium lattice positions. And as we saw earlier in silicon, so that's this light area up here on the sidewall, and also this light area up here on the surface perpendicular to silicon. So in general, the amorphous phase will be metastable, and its formation depends on the unit cell size, the complexity of chemical ordering, or the width of the limit phase field. So the more complex this sample surface is, the more likely it is that it will form an amorphous phase. So, for example, gold and your simple FCC, BCC metals, and even some HCP metals will tend not to form an amorphous layer, but silicon forms an amorphous layer because it's a more complex covalently bonded material. So again, not everything forms an amorphous layer, and this is on the left is copper, and on the right is silicon. And this is looking at a cross-section of a particular pattern. And there's evidence here for the redeposited material growing epitaxially on the copper, which showing that there is no amorphous phase here as a result of the ion beam hitting the copper, whereas this, again, light layer in between this very dark silicon layer and the intermediate redepth, which has a lot of gallium in it layer, shows that there is amorphization there. Okay, so how do we image with ions? We can use different detectors. We can use an ultraviolet Thornley detector. We can use channel electron multipliers, which are called CDMs or CDEMs, whereas basically we get an amplification of the signal. We can also use analytical type of instrumentation like SIM, VBS, EBSD, etc. So here's some different imaging detector modes. If you're in secondary electron mode, generally the detector is biased positive to collect the negatively charged secondary electrons. Again, these are emitted from the top 7 to 10 nanometers, so any sort of ion image, particularly secondary electron ion image, an ion-induced secondary electron image is going to be an extremely pure image, pure secondary electron image. Note, however, that the secondary electron imaging, ion-induced secondary electron imaging, is susceptible to charging artifacts. So here we see that these different regions here in the lower left and this leaf and some other features on this bug's eye are dark. And they're dark because they're charging, and so any secondary electrons that are generated from this surface are being pulled back down to this surface. They're not getting out because they're charging, and they're not getting to the detector, and hence they show up dark. Conversely, now if we switch to secondary ion mode, these are extremely shallow, emitted from only the top 0.5 to 1 nanometer, so they're very surface sensitive. But there's a lot less yield, so the images tend to be a bit noisier. And you also see that they're not susceptible to charging. So here we can see these features a lot easier than you can in this other image. Charging will also affect good milling as well as imaging. So here, if you've got a charging surface and try to FIB pattern on it, you can see that the charging surface can actually move the beam around. If you reduce or use a charge neutralizer, which is basically getting electrons down to the surface to neutralize this charge, you can then mill on features such as glass. Okay, ion-induced secondary electron signal gives you topography very similar to an SEM type of topographic contrast. That is, the incident angle. As the incident angle increases, the secondary electron yield increases. You also see that the yield will vary very much with different ions. And you see you have this crossover here at the low energy with helium and hydrogen and neon. The electron-induced secondary electron imaging versus the ion-induced secondary electron imaging is very different. You have to be careful with the interpretation. So here in the electron-induced secondary image, you tend to have your heavier elements are brighter, your lighter elements are lighter, and this is somewhat reversed in the ion-induced secondary electron image. Not only that, but you see that the ion-induced secondary electron image is can be much more susceptible to channeling contrast. Okay, so here in the brass down here, you're seeing a lot of different contrast here due to channeling. You see the lead here is pretty dark. The gold is the darkest, and the nickel here is actually darker than the copper. This is actually quite complex. And what you see is that the ion-induced secondary electron signal varies non-monotonically across the periodic table. We saw that also with the sputtering. So let me just go back a sec and show you this, because I didn't really point this out. Here we go. You see, with the sputtering, you see these peaks and valleys, and these peaks and valleys are due to the D-shell filling in the periodic table. And what you also see, if you look at the ion-induced secondary electron imaging, is that you get similar types of peaks and valleys across the periodic table. So this is some work that's in the literature, and this is some work that I did early on, and it seems to follow this complex relationship both between the sputter yield and the stopping power as well. So also, just to kind of finish this up, it's extremely complex. It's not fully known why these differences occur, other than there are definitely periodic effects or filling effects across the periodic table, which vary in a very complex manner between sputter yield and stopping power. Okay, here's the channeling effects. Now we're getting into an area where the material itself can very much affect what's going on. In particular, it can affect both the contrast as well as the sputter yield. So if we look at the critical angle for channeling, it has this sort of an equation. So for gallium ions into aluminum 111, the critical angles are 3.6 degrees, 4.0 degrees, and 4.8 degrees at different energies, 30, 20, and 10. And for gallium ions into nickel, critical angles are 4.6, 5.1, and 6.1 degrees at 30, 20, and 10 degrees. So you can see that by just looking down the different atomic structures down different directions, you can see different amounts of open areas. And so what this allows is the ions can travel deep down these channeling directions before they even start to interact with anything or hit anything. What that means is that, for example, along a particular channeling direction, the sputter yield is going to be less because the interactions are going to happen a lot deeper. In addition, your ion-induced secondary electron contrast is going to be darker here compared to, for example, here, where the gallium is going to run into something at the surface a lot quicker than it will here. Okay. What this also means is that you can change the angle here a little bit before you start to see effects change. So what this means is that this is silicon 110, but for example, this just meant that if you can tilt this a few degrees and still get a similar type of an effect before this changes. All right. So what this means is that you can get, however, really beautiful images using the ion beam for channeling. What this also means, however, is that you have to be really careful on how you interpret this, because, let me go back again, the critical channeling angles are small, like 5 or 6 degrees, 3, 4, 5, 6 degrees, and our definition of a grain boundary is sometimes 10 or 15 degrees or larger. What this means is that we can see differences in contrast that may or may not be due to differences in grain boundaries. They may be just differences due to strain. And in fact, it might be hard to see here, but if you take a look at the image that's on the charged particle optics book, this is actually an image that I took. So right underneath the columnar structure, first of all, you can see a fairly large grain here in the substrate, but what you see is differences in contrast there, and that differences in contrast is due to mechanical deformation, not due to differences in grains. So what this means is that you have to be really careful when you interpret some of these images, so you have to take images at various tilts to make sure that you're looking at differences in grains versus differences in just mechanical strain or strain in the material, or just slight differences in orientation. Okay, this is a xenon plasma FIB section, and then image with the gallium beam. You can see differences in material contrast. Note the very thick coating that you're able to FIB mill through the xenon plasma FIB, the columnar structure here in this plasma spray coating, and again, the differences in material contrast as well as the differences in grain sizes. The sputtering is also a channeling artifact, as I showed earlier. So if you're in a channel direction, you're not going to sputter as deep as you are in a not aligned or non-channel direction, just because the interactions are going to happen a lot deeper in a channel direction, and so you're going to get less sputtered particles coming out of the surface. Okay, FIB imaging resolution. Again, this is actually really important. One, because you have to understand when a vendor says what the FIB resolution is, you have to understand what they're telling you. Are they telling you a beam size? Are they giving you an image resolution? So you have to ask them what is it that they're actually measuring. And the hard thing about FIB or defining an imaging resolution with a FIB is that as you are imaging on something, particularly with heavy ions, you're also removing material. And this is a problem because you know that in general, when we talk about, for example, FIB-SEM resolution, you're going to get your best resolution when the contrast is higher, when you're collecting the most signal. But here in the FIB, the contrast, as you improve your contrast, your resolution actually goes down because you start signaling away what you're trying to measure. And this is also shown here. If you look at image resolution as a function of sputter sensitivity, the imaging resolution actually improves as the sputter sensitivity goes down, again, because you're not removing what you want to actually image. Okay, so you've got this problem where you're trying to measure something, but what you're trying to measure is actually decreasing. So the other thing that you should be aware of is how, again, resolution is measured. And typically what you want to do is measure the so-called rise distance of a single line scan or of a line scan. And typically you want to do this over thousands of line scans. Here, if we just take the rise distance, so this is just measuring the contrast across a particular line. And the rise distance, you also have to ask, what is the interval that they're using? So if I use 20/80, 20% and 80% of the rise, and I measure that, that distance is 1.8. If I say I'm going to use 35/65, 35/65 is going to make this number smaller, okay? So, again, you have to ask your vendors, how are they measuring the imaging resolution? What sort of statistics are they using? Is this just the best line that they're measuring, or is this over several different lines? And so, again, if you look at the rise distance distribution, 10,000 line scans at 20/80, you get 3.8 nanometers plus or minus 0.3 in this particular example. Whereas this single one might be just the best, and you can actually get a better number depending upon what you're measuring. So just be aware of that when you're measuring imaging resolution with the FIB, how they're doing it and what's actually being done. Okay, so again, just an introduction to prototyping and automation. One of the first things people do when they get a FIB is FIB mill their logos into stuff. This is always useful to impress administrators and managers. Look what our multi-million-dollar FIB tool can do. But this is also always good for, you know, to show off what you can do with your FIB instrument. And of course, if you can FIB mill logos and things, then you can also FIB prototype. So someone asked the question, sorry, in practical applications, do you calculate these angles before imaging or just soak the sample until the contrast is good? So in a practical application, so you can calculate those angles for any material, but the way that you know, for example, whether or not you've got a grain boundary versus just strain, if we go back to the imaging contrast, sorry, just talking about ion channeling contrast in general. Yeah, sorry. So this equation you can calculate for any material, right? So you know, but typically it's going to be in the, you know, sub 10, less than 10 range typically. And you know, for grain boundaries are typically defined by 10 or 15, 12 degrees, however you want to define a grain boundary. So if you tilt only a few degrees and you see the contrast changing, then you know that it's more strain related versus you've actually got a grain size related, right? So that's how you can really define whether you've got grains or just strain, for example. Okay, but typically you can. There's no reason why you can't do, you know, plus or minus 5 or 10 degrees and find out really quick what you've got there. Okay, so there's our prototyping. Gas injection systems, typically we're using a power organic gas for deposition. We're using reactive gases to etch. Gases are delivered to the sample surface with a needle, generally in close proximity to the surface. And how the gas interacts with the sample will determine whether you've got deposition or enhanced FIB-SEM. So there's a lot of different gas injectors out there for deposition. You can do platinum, tungsten, SL2, carbon, gold, enhanced etch. You've got the neon fluoride, range of other gases. There's a lot of vendor-only products or third-party vendor products out there for gas delivery. For deposition, the idea is to place the gas, insert the gas needle. This is generally set to be 50 to 100 microns from the sample surface. You heat up the gas to sublime the material, and where the gas, this gas will go on for several hundred microns, if not longer. Okay, so wherever you raster the beam, whether it's gallium or xenon or even your electron beam, you're going to crack the gas, resulting in a deposit, and then whatever doesn't get decomposed will be removed via the vacuum chamber. All right. So there's all sort of as well. We'll talk about more about that in a little bit. There's all sort of manipulators, probes, and testing for both in situ and ex situ type of analysis. We'll go to talk about that later. And this just shows you a really nice start to finish analysis of how you're going to use your FIB. You can computer automate and script the FIB for making test samples. You can then put an in situ probe to mechanically deform the sample. Then you can make a TEM section out of the sample to look at deformation mechanisms. You can look at stress strain curves, etc. So this combines a whole bunch of stuff that you can do inside of a FIB. Remember, FIB sources, ions for different applications, and in summary, basically this is all that we covered in here. All right, so let's take a 10-minute break, and we'll combine. Is there any questions? I'll just hang out for a minute or two. Any questions so far? If you have any questions, type them in. Let's take a 10-minute break. So it's currently 2:30, so let's reconvene at 2:40. This is Eastern time. All right. Okay. Thanks, everybody. Ion beam interaction volume, and the answer is yeah, sort of. So if you go to shrim.org, you can download shrim or trim, and there's a lot you can do with it. You have to be aware of some of the limitations. One, it uses an amorphous or assumes an amorphous sample, but I like to use it as a sanity check, in particular for what's going on. So it's really good for calculating ion residues, sputter yields, and et cetera, and some other types of things. Okay. All right, so let's continue. We're going to talk about nanofabrication and prototyping. Again, there's a lot of references. Some of the references I showed earlier, but some really good references here. This book on the left, Nanofabrication Using Focus Line and Electron Beams, and the MRS Bulletin in particular. The most recent one talks about direct rate patterning using ion beams. And again, some of the other references have some things screened in them as well. Okay, so we're talking about a focused ion beam, hence the name, of course. And so what this implies is that we have to move the beam around to actually remove and dig holes. Okay, so to move a beam around, if we consider a pattern with a length and a width, the beam has a certain spot size D. The pitch or the step is F. And if we think about having to mill something or remove material, there generally has to be some sort of overlap of the beam with the previous beam so that you remove material instead of, for example, just drilling holes in a material. So we can define the beam overlap or the spacing or the step size or the pitch size. And of course, if you change one of these things, you automatically change the other. So a 50% overlap or 50% spacing is generally used for sputtering. And here we see what this 50% overlap looks like. At 0% overlap, the beam is just touching, the one edge of the beam is just touching the other edge of the beam. And at minus 50% overlap, this is actually analogous to a 200% spacing. So this is generally used for large gas patterns. Again, the 0% overlap is generally used for etching or depositing. And so we use the overlap or the beam spacing differently depending upon what we want to do, whether it's milling, deposition, or etching. Okay, some other parameters, pitch or the step size is the actual distance between pixels. So again, a change in beam size for the same pitch will change the percentage overlap or the percentage spacing overlap. We can change the pitch in either X or Y or both. Some other parameters, dwell time, is just the amount of time that the beam sits on any single pixel before moving to the next pixel. The passes are repeats, so the number of times the beam hits the same pixel within a pattern. And the refresh time is the time from the last pixel in the pattern back to the first pixel when multiple passes or repeats are used. And all of these functions are extremely important depending upon the function. So the pattern shape types, there's spots, lines, polylines, rectangles, squares, trapezoids, circles, ellipses, annulises, text, stream files, bitmap files. You want to be able to mill the inner portion or the outer portion of the shape. You want to be able to do mathematical functions, that is add or subtract shapes, shape arrays, ability to save and relay shapes, etc. All of these are just add to the ease of use of the instrument. The question, does a typical system have a pixel size that is much smaller than the beam diameter, or is it comparable in size? So yeah, the pixel size can vary. The pixel size can vary depending upon the pattern and the field of view and or the beam diameter. And so when you're milling, for example, a bitmap file, you have to consider how big you want to make that relative to, for example, what you're trying to mill. So the pixel size and the beam diameter are definitely independent of each other, okay? Or they can be independent of each other. Scanning speed. You can scan in a line, in a serpentine, from left to right, right to left, up to down, down to up, at a preset angle, inner to outer or outer to inner. And we'll also talk about serial or parallel milling and when that's important to use. So here's different scan types, and this shows this extremely well with a single type of beam or single type of pattern. So here we're using a pattern, and the pattern is defined by an outer diameter and an inner diameter. And depending upon how we scan the beam will very much depend on what our ultimate shape results in, because this depends on where the sputtered material will redeposit, okay? So if we have this outer diameter and inner diameter, and if we mill from the bottom part of the sample, bottom part of the pattern to the top, initially we start to mill perpendicular to the sample, and then we've created a little bit of an edge with that first pass. So with each subsequent line of this mill shape, the sputter yield will increase and our pattern will get deeper and deeper and deeper. But as we know from here to there, the sputtered material has to go somewhere, and basically it goes behind. And so we'll wind up with a deeper part of the pattern up here compared to where we started with a not so well-defined center. Okay? If we mill from, let's put my glasses on to see this. Okay, if we mill from outer to inner, we're starting from, inner to outer, we're starting from the inner portion, and we're milling in a circle, concentric circle, milling to the final edge. The sample will have a not very well defined middle area here, and the pattern will get deeper out on the edge because this is where the final position of the beam will be. If we go inner to outer and then outer to inner and do this over and over again, then we get a flat surface here with a little bit of a button kind of a shape in the center, little pillar shape in the center. And again, because we're going inner to outer, outer to inner, and we're alternating this, we get a relatively flat bottom surface. And then if we start from the center and we go, we start from the outside and mill towards the center, then the thickest part or the deepest part of our milled area is going to be here towards the pillar, and we're going to be left with this little bit of V-shaping here of the pillar, which again is due to redeposition. So, in fact, this is the type of pattern that we use when we want to make anechoic samples, for example. But you can see how the scanning parameters of the same shape varies what our ultimate mill pattern looks like because of where the sputtered material and ultimately the redeposition goes. Okay, so there's a question: when signaling two separate boxes, is the beam moved quickly across the intermediate in between boxes, or is the beam blank? That's a really, really good question. So the answer is that the beam will always drag a little bit from one pattern to the other. And so, does everybody see what that question is? So let me go, let's see. Let me go to the next slide and see if I can, yeah, it's, I don't know if I have a good example of this, but, so let's just assume that we're talking about these four different patterns. So the question is, if I mill here and then jump to this one, and then jump to this one and jump to this one, will there be any dose given to anything in between? And the answer is inevitably yes. And so when you're trying to mill something, if you're trying to mill dots, for example, but hit one space over and over and over again, you have to be careful in what direction you specify that pitch, because the beam will ultimately, a little bit of beam will ultimately drag. Even though you've got a fast beam lengther, you will see that there's a little bit of slop, and you'll actually see some ghost lines, or in some cases even worse than ghost lines, of the beam jumping from one beam to the other, from one pattern to the other. So yeah, you'll actually get some ghosts from one pattern to the other. So you have to optimize that and be careful of how you program that, for example. Okay, so there's different ways that you can change the scan direction, angle, and pitch. And this shows, for example, that you can change the vertical pitch and the horizontal pitch or step size independently, or you should be able to anyway. You can change the scan direction, you can change the scan type, et cetera, et cetera. So there's a lot of flexibility in what you can do there, or at least there should be. This is a filled pattern versus an outline pattern. So for example, if you specify a pattern, you want to mill the inside of it, or do you want to mill the outside of it, and what thickness of the outside of it. There's different things that you can do there. And then this is serial versus parallel milling. And this is really important in the case of when we, for example, undercut a sample, particularly for TEM sample prep. We always want to do the undercuts in parallel mode, or we combine them so that they're basically one pattern. So serial versus parallel milling, let's say we have 3 different patterns. This square pattern, this multi-angled pattern, and this oblong type pattern. So in serial milling, we're going to do this pattern, the square pattern to completion, and then we're going to do this second pattern to completion, and then we're going to do this third pattern to completion, and all our milling will be over. In parallel milling, I'm going to do one entire frame of this first pattern, then I'm going to jump and do the one entire frame of the second pattern, and then I'm going to jump and do one entire frame of the third pattern, and I'm going to do it n number of times, okay? So the thing is, in parallel milling also, all of these, the number of passes of all of these have to be the same, okay? Whereas if you do these 3 patterns independently, the number of times, the number of passes can be independent because you're doing one completion and the second one and the third one. Okay? The milling duration can be defined by the total time per pattern, the depth via some material file that may be built into your system, or you can define the dose, or you can define the number of passes or repeats, which of course will, you change any one of these things and all these others will change because these are all tied to each other. Okay? So if I define a depth via a material file to be, say, 5 microns, this will automatically define the total time per pattern. We'll already define a dose based on the size of the pattern, and we'll then define the number of passes based on the dwell time. If I change any one of these, then these other things will change because these are all tied to each other. So something that I've noticed is, and I'll call this signaling with better columns in quotes. So in quote older columns, 50% overlap is the norm, okay? So 50% overlap with an old column that has sort of a, we'll say worse resolution, a bigger beam, is sufficient so that the distance between the beam tails and the center of the beam hotspot is pretty small, so that you'll get some pretty good, basically removal rates will be very similar. But in some of the newer columns, what I've noticed is that a 50% overlap, because the beam density is much higher, the beam is actually better. But what happens is that then the distance between the hot spot of the beam and the beam tails is much greater. And what you wind up getting, if you look at the cross-section, is you actually get these curtaining artifacts just due to the beam effect itself. Okay? And these curtaining artifacts will appear on your sample surface, which is not particularly good. And so the way to get around that is you can do one of two things. One, you can defocus the beam to actually spread it out so that you get something more like this. Or the other thing that you can do is go to 85% overlap, for example, such that the position between the hot spot of the beam and the beam tails is about the same as what it was on an older beam. So the problem, not necessarily a problem, but you have to be aware is that when you change this to 80% overlap, you're using more patterning overhead in the sense that now I need more pixels here, or the beam has to hit more spots from here to here versus, for example, an older beam where the beam itself is larger. Okay, does that sort of make sense? But anyway, you just got to be aware of that. So some of the newer columns, the vendors specify that you need to go to a larger overlap to prevent current heat of the beam itself. So it's just something that you should be aware of. Okay, so again, we hit on this before, what limits ultimate resolution in FIB milling. One, the beam size, of course. We talked about redeposition. This limits the aspect ratio that's achievable and also affects the shape of the feature, as I showed you earlier. By just milling the same pattern in different ways, you'll get very different types of shapes. The ion mixing also affects the V-shaping, and as well as the ion-solvent interactions. Remember, I just showed you this movie earlier that showed when you've got an incoming ion, this can generate sputtered particles at some distance from where the incoming ion is. There goes the particle. And so you might not be able to generate, for example, a certain size hole in a certain material, but you can generate it, for example, in other material. Here's some work I did a few years ago with Barbara Garrison and others at FBI when I was there. This is a molecular dynamic simulation showing the ion mixing at 2 kV and also 30 kV. To me, what's interesting about this is that if you can get a monochromated 2 kV beam, you'll have less ion mixing than with the 30 kV beam. You'll actually get a lot less damage and a lot tighter beam spot, although the sputtering is a little bit less. But you can get some interesting, probably, results from a monochromated 2 kV beam, which of course doesn't exist yet. But that's on my wish list for the ion beam folks to develop. The FIB milling also varies with target and beam parameters. So, for example, if you just change the dwell time, you're going to see a much wider slot, 30 nanometer spot with a larger dwell time than if you just decrease the dwell time. And this is analogous to, for example, if you're just trying to dig a hole in your backyard, you've got a shovel, you start digging a hole. At some point, you can only go so deep without whereby you can't get the material out unless you make the hole bigger. Okay, so that aspect ratio is going to be limited for a specific ion target species at a specific energy. And as I showed you earlier, depending upon how you scan the beam, you'll get different, the sputtered material will go to different places, resulting in redeposition. So the redeposition also affects what sort of milling artifacts you're going to get. If you try to mill the same pattern with 500 picoamps versus, for example, 2 nanoamps, the redeposition is going to be an issue at higher beam currents, and this is going to affect the quality of the shape. So if you're trying to mill something, you know, with a FIB, it's always, do I want to do it fast and sloppy, or do I want to do it slow but really neat? And those are sort of always the trade-offs that you have when you do FIB milling. Here's some work by some authors that actually simulated focused ion beam milled features by incorporating redeposition model and where does the sputtered stuff go so that they can accurately predict what kind of shapes that you'll ultimately get. Prior to this, people would basically do trial and error types of shapes, types of features. I want to mill this Fresnel lens, I want to mill this whatever feature, and then ultimately not get what they were hoping for, tweaking things on the fly. This model incorporating the redeposited material from sputtered particles will actually, if you incorporate this into a model, you can actually reproduce this quite well and actually predict what your features will look like. The milling profile will also, of course, depend on your incident angle, so which is directly dependent on your ion file interaction. So if you FIB mill at 52 degrees versus 0 degrees incident angle, obviously this is going to affect the range and also your ion file interaction, so you'll actually develop a deeper cut, for example, at 52 degrees versus 0 degrees. And this also shows some work that I did several years ago, showing what happens when I mill up a slope versus down the slope versus across the slope. So milling up a slope, because the interaction volume or interaction species or your collision cascades are always below basically the beam, the collision cascades are being pushed down the angle. You're always creating sort of a new feature. Going up the slope, it's quite shallow, but if you mill down the slope, you're always working on a piece of the collision cascade that was always basically you're always overlapping the previous collision cascade, and so you can actually go a bit deeper, and then across the slope, of course, generate a pattern which is consistent with the initial slope. So FIB milling of 3D structures becomes really easy if you define bitmap files, for example, where you can predefine what the dwell time is based on a certain grayscale level. So in here we've just got 3 different grayscale levels: white, black, and gray. And so by FIB milling that, we can immediately generate a 3D structure where the dwell time for each of these different grayscale values correspond accordingly. So here, if we draw a line across there, we can see that the white area is the largest dwell, the gray is some intermediate, and the black is no dwell at all. So some people have actually made businesses out of this and/or art. So here you see these are art castles and grains of sand. There's a company here that can personalize your diamonds for you. They can do pictures or sayings or text or whatever. And they'll also give you this little viewing thing so that you can view exactly what you want on a diamond. Now, it turns out that FIB milling diamonds are actually also have been used in the past to identify diamonds for example, just for putting identification marks. They're actually better than laser inscribing because the laser will actually discolor the diamond where the FIB will not. So you can combine scripting with multiple patterns. So you can just combine bitmap files with scripting and image recognition. So here's an example of there's an image recognition file and scripting multiple images of this bitmap file. People always ask, how do I FIB mill organic materials and polymers? And you can do this, in fact, with a cryostage or without a cryostage. Now, without a cryostage, you have to now consider what material you're FIB milling and what is the width of the collision cascade. In this case, the collision cascade for polymers is generally going to be much wider because these bonds tend to be a lot weaker than in organic materials, and so you're going to generate a lot more recoil. And so the conventional 50% overlap that we use in, for example, silicon material file isn't going to work for some of these polymers because you're going to have overlapping collision cascades. And if you have overlapping collision cascades, that means that those atoms will never have any time to relax. Those recoils will always be in motion. And in that case, you will get local melting and deform the polymer where you FIB milled that particular polymer. You're not going to heat up the entire polymer, but what you're going to do is basically locally destroy the polymer surface. So all you have to do is go to very large overlap, very large negative overlap. So you want to step the beam much further apart than have a 50% or zero overlap. So if you step the beam much larger, at a much larger pitch, that's a much larger negative overlap, you can avoid the overlapping collision cascades, overlapping recoils, and FIB mill the polymers just fine without a cryo sieve. So here again is examples of FIB milling cutting tools. So if you can think of it, you can FIB mill it. These are kind of micro cutting tools, if you will. And again, a lot of this is done by trial and error. If you can now incorporate these other models into it, you can save a lot of time. Again, in fine soil, Fresnel fringe type effects, type things, you can FIB mill. And this is from this is originally from JVS2, but also in the MRS bulletin, showing the combined use of beam shift as well as stage shift for large area patterning. Okay. And then again, using your ion-solid interactions, you can very accurately predict or understand why it is you get better or smaller milled features with helium and gallium versus gallium. And this is work by John Noddy. And if you just plot basically the sputtered particles and where they're coming from the top of the surface, as I showed you earlier with Barbara Garrison's movie, you can see where these sputtered particles come from. And this is just using shrimp calculations. You can see that for helium, the amount of sputtered particles, first of all, the sputter yield is less because you get electronic stopping instead of nuclear stopping, but the number of particles are less, but the distribution is much tighter around where that center spot is, okay, where your ultimate beam position is. The heavier gallium is going to generate a lot more recoil. This is going to generate sputtered particles from much further away from the center position. So assuming that you've got the same beam size between helium and gallium, you're going to be able to FIB mill a much smaller feature with helium and gallium. Now combine the fact that the helium beam itself is going to be an order of magnitude larger, an order of magnitude smaller than gallium. With the combined fact that the sputter yield of helium is much lower as well as much more confined to the center point, you're going to be able to FIB mill much smaller features with helium, with the lighter helium than with the heavier gallium. Okay? And this is emphasized again in this work here by this Linded and co-authors at Intel, as well as Zeiss. So this is a gallium FIB. This is a helium ion microscope. You can see that you've got much better defined features using the smaller mass helium ion compared to the larger gallium ion. Okay. Not only that, you can get higher aspect ratio features in this gallium on this edge of the surface. In addition, you can also just use the helium to etch, not necessarily etch, but just photolithography type of application. Okay. So let's go into patterning now with gases. There are both deposition and etch mechanisms. You can have gas absorption. And again, how this gas, added gas, interacts with the beam will depend on whether you get deposition, whether you get etch retardation, or whether you get enhanced etching. All right, so again, showing this slide, you've got the incoming gas injector nozzle. It comes in close proximity to the sample surface, about 100 microns or so. You've got your, in general, organometallic gas. You heat it up, and this sublimes the gas, sublimes the material, resulting in a gas. When you open the valve, this gas goes everywhere. And I want to make a point here that this deposition is line of sight. So if you have a sample with a lot of topography and the gas can't get to the region that you want to deposit on, then you're not going to form a good deposit. So the gas has to be able to get there. It has to be line of sight. So if you're knowing something that has a lot of topography, in some cases you want to either turn your sample at a particular orientation relative to the gas injector system, or you want to just make your pattern, again, sort of in line with where the gas is coming from. Okay, so where you deposit or where you scan either your gallium or your electron beam, you're going to crack the gas, resulting in a deposition. Okay? And remember, for heavy ions, you've always got the competition between deposition and sputtering. All right. So you're going to have this master growth rate curve, and for deposition, the curve looks something like this. So you're going to have your deposition rate and your ion beam current or pattern area. So as you use a particular beam current, use a very small beam current, the deposition will be very efficient, or the deposition will be very good, but it's going to be very slow. So as you turn up the beam current, you lower the beam currents, the deposition rate is going to increase. And there's going to be a sweet spot here. This is your optimum deposition rate, optimum beam current, and then you reach the so-called gas depletion range. And in the gas depletion range, what happens is that, as the name implies, there's not enough gas there for deposition to occur. So this occurs one of two ways. One is obviously if you've ever operated an instrument and you're not getting etching, you're getting milling. One is because you can be just out of gas. The two, you can be using a beam current that's way too high for the pattern that you've defined. And so there's generally, any vendor will give you generally a formula to use. And that formula might be, for example, 2 to 6 picograms per micron squared for the case of platinum or carbon in some materials. So the important parameters for gas deposition are the pressure, flux, and sticking coefficient. In general, you can't change these. These are vendor specific. In some cases, you can change the pressure by just changing the temperature of the gas. But the ion beam parameters are something that the user is going to have to pick correctly. And this is generally the dwell, the pitch, the refresh rate, and of course, what ion beam current do I even use for that particular pattern. So important parameters for deposition, you want very short dwell times compared to milling. And this is because you want, you don't want to mill through the gas. You want a chance for the gas to replenish itself. You want a very large pitch compared to milling, so generally this is going to be 0% overlap or larger, more negative. And you want a large refresh rate, again, because you want a chance for the gas to adsorb back onto the sample surface before you hit that pixel again with the gas. You can also FIB deposit from bitmap files. So here shows an example of this is what the bitmap file looks like, and this is what the subsequent deposition look like. The one thing that you should be aware of is that deposition can cause damage because on the onset of deposition, you still have the interaction of that energetic ion with your sample surface. And you've got that onset of competition between deposition and milling. So if you take a look at the image on the left is for 30 kV gallium on silicon, and you see about 50 nanometers of damage here, which is consistent with 50 nanometers of 30 kV gallium on silicon surface. If you go to 5 kV gallium, that damage is reduced. Now, if we use electron beam deposition on top of silicon and cross-section that, this bright area here is consistent with just native oxide on silicon. And so if you're really worried or want to analyze the very top surface of your sample, you can do one of two things. You can don't even turn on the ion beam if you have a surface-sensitive sample. Deposit the region of interest with electron beam deposition first, and then you can use ion beam deposition on top. And the reason why people use both is because electron beam deposition is so slow. So you can get about 100 nanometers of electron beam deposition on top of your sample, put ion beam deposition on top of that, and that will prevent ion beam deposition damage to your top layers. The other thing that you can do is protect your top layers through a coating, through a sputter coating. But you have to be careful of sputter coating because if you don't use a continuous sputter coating, you can get ion beam platinum damage through the coating. So this is silicon. This was deposited with gold palladium. Gold palladium goes down as islands, and then this was FIB deposited with ion beam platinum. And you see that you can actually get damage of the 30 kV ion platinum through the islands. So if you're going to put coating on something, make sure it's a continuous coating. Okay? All right. You can also deposit 3D structures by basically making a cantilever structure and overlapping the beam slightly with the previous position before it. And this, you can build up 3D structures doing this. So this is an example of 3D carbon deposition. This is a micro bellows. This is a micro wine glass, and I believe this wine glass was in, or is still in, the Guinness World Book of Records for the smallest wine glass to be used. Later when I have a glass of wine, however, I want a glass that's a bit bigger than this. So. All right, you can also do what's called free-space wiring. Again, this is just 3D deposition out of the plane of the substrate. So there's all sorts of things that you can do. Okay. You can also deposit with helium and other ions. And of course, with helium, because it's a smaller probe, smaller beam, you're going to be able to deposit much smaller features. Okay. And then because of the so-called reshaping that you get as a result of redeposition during signaling, again, remember the shovel and dirt example before, that you're going to reach a point where you're not going to be able to signal anymore. There's going to be a limit in the aspect ratio. There's going to be a limit in the depth that you can mill due to this redeposition and aspect ratio limit. Okay, so here's gallium sputtered zeolith as a function of different patterns. If you incorporate now a gas, which will help which will enhance the sputter yield. Basically, this helps to pull the sputtered material out of the trench so that you don't get redeposition. You can actually FIB mill deeper and reduce the V-shaping, which is limited by the redeposition of the sputtered material. Okay, so the enhanced etching increases the sputter yield by getting this material, by acting with the material, making it volatile, and pulling it out of the trench. All right. You can also use enhanced etching for removal of certain materials over another material. This is called selective etch. For example, this is selective removal of PMMA on aluminum. So here we can selectively remove, for example, the PMMA leaving behind the aluminum structure. You could signal diamonds with selective carbon mill or water etch. This again helps to enhance the etching. So this is the same pattern with and without the water source, and you can see that you can go a lot deeper and get a lot better surfaces. Okay, so to sum this up, digital patterning is really useful for prototyping. Ion beam and electron deposition of metals is possible. You can get ion beam assisted enhanced milling or selective milling is possible. And you can model redeposition to the patterns to avoid firing or experimentation. All right. So let's just take a little break and let's convene at 3:30. And if anybody has any questions, again, please don't hesitate to put them in. So we'll just take a short break and we'll come back for the next lecture. Thank you. Okay, everybody. Welcome back. So let's move on and talk about 2D and 3D specimen preparation, and then our last lecture will be on TEM specimen prep. So, so this is the FIB milling versus Italian zero cutting example. And over the years, people were upset that I was calling it a hero. So I had to include sub grinder, hosey, blimpy, baguette, ciabatta, wedge, po' boy, Gatsby, zet, Cuban, muffalata, panini, baguette, French dip, and of course sandwich. But the idea is for a cross section, you're taking your knife and you're going across multiple different features. And of course, if this is an Italian hero, you're going through the bread, the tomato, the lettuce, the ham, the capicola, the mozzarella, provolone, etc. So that's your cross section. That's a transverse cross section. If you want a longitudinal cross section, you can cut it the other way across the sample. And if you want a plan view, you can just take your FIB and cut out the tomatoes, for example. But anyway, the idea is that with the FIB, you're cutting through different materials sequentially, and then we're going to look at it with the FEM or TEM for that matter. Okay. It is also possible, of course, to FIB mill parallel to interfaces. If you're FIB milling parallel to interfaces, you have to remember that one side of the sample is probably going to FIB mill at a different rate than the other side. You can also possibly get certain artifacts, so you have to be careful there. But your rate limiting step there in achieving the depth that you want is going to be the slower milling material. Okay. As I mentioned earlier, if you want to FIB mill across a region of interest that has that's right on the surface that can be damaged with the FIB, there's a number of ways that you can protect it. One is with electron beam deposition prior to FIB deposition. One is with a coating, but make sure it's a continuous coating. The other thing that you can do is to use a Sharpie pen, which is basically just a conductive carbon particles inside of a polymer. a solvent. This is your permanent ink marker, for example. Or you can also spin coat conductive polymers on top of the region of interest. So there's a number of ways, things that you can do to protect your sample prior to FIB milling. So the basic idea for 2D FIB sections is to mark your region of interest with platinum or carbon or tungsten, whatever you have available for you. And this does two things. One, obviously, to mark where you want to cut. It also protects the underlying region from being sputtered away, assuming that's not your sensitive region if you're FIB depositing. The other thing it tends to do is it tends to smooth things out a bit. You can see this particular sample has a little bit of a rough surface, and so this tends to smooth things out with age and curtain artifacts. So the idea is to make your first cut somewhat away from the original deposition, and the idea is to just make the cut. In this case, this is called a stair-step cut, or you can FIB mill line by line using so-called clean cross-section or line-by-line milling. And the idea is you don't have to cut away the entire section here because you're not going to be able to see into that anyway. So this just saves time by milling the so-called cut that gets deeper and deeper and deeper towards the region of interest. So you use a large beam current. This can be tens of nanoamps for the rough mill. And as you approach the region of interest, you use finer and finer beam currents until you do a final polish somewhat less than a nanoamp or less, depending upon what you want to image. Okay. And here's an example of the FEM image of a FIB cross-section, courtesy of Joe Michael. So here you can see this somewhat rough surface, which again is evened out a bit by the platinum. You can see also this is E-beam platinum on top because you didn't want to damage what you were looking at right at the top surface. Copper sulfide, gold marker, another copper sulfide, copper. You see these different layers. The total time should be anywhere between 10 and 30 minutes to make one of these FEM type processes. It should be pretty quick. Okay. The other thing that you can do, particularly in the semiconductor industry, is to use enhanced etching. This can, or sometimes called delineation etch. And what this does is preferentially mills different materials. What this also does is create edges, so that if you take a secondary electron image, FEM image, you can actually see the different edges. In addition to the material contrast here, brings out these edges quite nicely so that you can collect FEM images after you do this FIB milling. Okay. I showed this to you earlier. You can also FIB image your 2D section. This was on a FIB type instrument, but you can also use the FIB on your instrument to image inside the trench. This generally requires a 180-degree rotation, sample rotation to look in there. On a single beam FIB, this just requires a single tilt. Again, it just depends on the geometry you're using. But the advantage to FIB imaging a FIB cut, again, is the unique material contrast as well as the unique channel contrast that you get using the FIB itself. All right. So the idea then is, of course, if we can create a 2D section anywhere, we can then extend this to taking multiple sections and create a 3D volume of information. And in fact, the first 3D FIB work that was done was done with FIB, whether it be FIB imaging or FIB-SEM, or in the case of FIB Auger, and this is all in that sort of FIB book. So Robert Hall and co-workers showed that you could take a slice, image with a FIB, take another slice, image with a FIB, and at the same time collect SIMS information to create a 3D volume of material. And Ed principally showed that you can collect Auger information on each of these FIB slices, collecting 3D information as well. Note that because we're FIB imaging, FIB sectioning and then FIB imaging, the 3D FIB work is destructive. So once that sample's gone, it's gone. There's no way to come back and look at it. Now, for 3D FIB work, there's a lot of work that goes into the initial sample setup. Because you want to avoid sputtered material redepositing on the sidewalls, you have to really open up the area. So this is from top down. This is the region of interest, okay? And so all of this material around here has been FIB milled away. So that when you continue to FIB mill and take a slice, that sputtered material will accumulate here and not block your region of interest. Okay? It's also necessary to use fiducials so that when you FIB mill each area, the beam knows where to go to the next slice. And there's also fiducials that you can use for SEM imaging so that it goes back to the same slice as well. So it's also often useful to use fiducials on the top of your sample surface. This is so you can precisely monitor the slice thickness. So from the top here, you can make 2 lines where theta is the angle between the lines. And then D here, you can get an accurate measure of the slice thickness by how D changes as a function of time. And as you FIB mill through the structure, then obviously W is going to decrease, and that will also then, of course, decrease D. You can accurately determine what the slice thickness is instead of relying on the slice thickness that you set into the software. Reconstructing and spending probably for every hour of instrument time, there can be up to 10 hours or more in doing the reconstruction. And this is also often the difficult time. Not only just the reconstruction, but if you want to do any sort of segmentation and analysis, this can take a significant portion of the time. This is the so-called banana cucumber problem and why it's important to use fiducials. If you serial slice through a banana and use the feature itself to align the cross-sections, so this is the actual serial sections that you get. If you use the feature itself to do the image alignment, you'll actually wind up with a feature that looks like a cucumber instead of a banana. Okay? So if you use a fiducial mark, this is a top-down fiducial mark, and in the slice you'll see a little piece of that fiducial mark in the image. If you use the fiducial mark to align the region of interest, then you will retain the banana shape, and you will actually reconstruct a banana instead of a cucumber. So this is why it's very important also to use fiducial marks in the 3D reconstruction. So this is some work I did several years ago, a few years back, using multi-signal SEM imaging on a single slice. So this is bone on a dental implant. So this is the secondary electron imaging is on the left, the backscattered electron imaging is on the right. And what you see is that the different signals will give you different information. Obviously, you get the really nice material contrast on the right, so you can see the bone, you can see the ceramic coating, and then you can see the titanium implant. Whereas the secondary electron signals shows the edges of the pores in the ceramic coating very nicely. And what's so useful about looking at this 3D imaging is that here, for example, you can see that bone has grown into, both down into and then laterally into the ceramic coating. If you were going to make, let me just stop this. If you were going to make a single cross-section here, you would say, how the heck did this bone get below the surface? But it gets below the surface because this pore is shaped like a volcano, and it actually grows down and laterally. And so now you can play, of course, games with how you reconstruct the model. You can see the pores from top down, but it actually is at the surface much smaller diameter at the surface than it is within here, and so you get bone growth actually down and into the surface as well. You can also put other detectors into your FIB-SEM and therefore not only collect SEM images, but also different signals from either the SEM or the FIB, for example. So here's was the first example of 3D FIB-SEM EDS by the work at the group at Sandia. So this is a copper-silver material showing the differences there. So you have to, again, collect at each slice, you're collecting EDS signal, and you're mapping that and then reconstructing the map. You have to be careful when you do 3D FIB-SEM and EDS because typically the imaging conditions that you use are not necessarily going to be good enough for collecting the EDS characteristic X-ray signals that you want to use. So work from Team Scott has shown that if you use, for example, 5 kV imaging, which many people might do, or even lower energy imaging, you're not going to be able to detect the characteristic X-rays that you need. But if you use 20 kV, for example, SEM, you're going to smear out the features that you want to get because the interaction volume from 20 kV electron beam is going to overlap with different smaller features. So you have to be really careful in how you define your SEM acquisition of imaging versus EDS technique. And ideally, what you would like to do is collect a bunch of images, and then maybe collect one EDS scan and then continue on. So you can also do 3D FIB-SEM EDSD. So here we're collecting, again, this is courtesy of Joe Michael. So at each scan, he's collecting an EDSD scan to look at the crystallography. In this case, these are whiskers drawn on a copper substrate. The EDSD geometry inside of a FIB-SEM doesn't always lend itself very nicely to what's going on. And so you see that this has to be done on the edge of a surface. So there's a lot of pre-specimen preparation involved. This has to be done on the edge. You have to open up a lot of material with the FIB so that you won't get redeposition and material blocking. There's a lot of different fiducials that you have to use on top of the sample as well as different features. And because the EDSD camera is generally underneath the ion beam on the column, this results in rotations of the sample for ion beam between the ion beam milling and E-beam acquisition. And that also means that you need use fiducial marks to mark so that the E-beam and ion beam can go back and forth without any difficulties. So this is data reconstructed from 75 slices, 200 nanometers thick. Each pixel is 200 nanometers cubed. So the total time is 48 hours. So that's a lot of instrument time. These types of things are generally done over the weekend, for example. And again, when you start to consider how many slices there is, what is the amount of time that each beam, electron beam, spends either collecting an image or an EBSD pattern or an EDS pattern, you can get into tens of hours of acquisition times. And so this can be quite lengthy. Okay, so how do we do 3D reconstruction? Again, there's sort of image correction things that you can do. You can correct the shadowing, you can remove curtaining, although I'm not a big fan of how that's done, but I'll leave that for another day. You can control brightness contrast. There's the image alignment registration, which I mentioned is the best way to do that is with a fiducial mark. There's cropping, there's basic noise reduction smoothing, there's segmentation, there's volume rendering, there's quick and dirty visualization, maximum intensity production. And again, all of this can be many more hours spent on this than the actual acquisition of the 3D data in and of itself. So this was just a very quick introduction as to what you can do. Obviously, the 2D FIB, 2D FIB-SEM is used extensively. 3D FIB-SEM is being used a lot more now. It is non-trivial. It definitely helps in yielding information that is not evident with conventional 2D analysis. It's extremely time-consuming to set up and also time-consuming and can be expensive in the acquisition. Then all the offline rendering, reconstruction, and segmenting is very time-consuming as well. So anybody who has done this, you know that this is often given to graduate students and postdocs to do. And remember that 3D SEM imaging conditions may not be ideal for 3D EDS or 3D EBSD acquisition for that matter. And I just wanted to add that there are multiple different programs that are available to do this 3D rendering and reconstruction and segmenting. There's vendor-specific things that are available, stuff like a Mira or a Viso. CG is formerly ImageJ, that's freeware. There's also iMod, which is freeware. And there's a relatively new company called Object Research Systems based in Canada. And some of the folks there were previously from Amira and Viso, so they have a lot of experience in doing 3D FIB-SEM reconstruction as well. Yeah, thank you for that other example as well. So, where is it? Gideon? Is that how you pronounce it? Thank you, Charles. So, any questions on that? There's not a lot there. Obviously, it's oh, chats can't see. By the way, attendees can't see chats from the attendees. I think if you say to other attendees, you should be able to, if I'm mistaken. But anyway, I think I've been repeating what the questions are, so, or comments. Any questions on that? I just wanted to go through that relatively quickly because the last thing I'm going to talk about is keeping on sample prep, and that's going to take up the most of the time because I'm going to spend a lot of time on that. Okay. All right, so I have 3:52. Let's just take a 8-minute break. That's okay. We'll come back at 4 o'clock, and I'll try to get through the TEM sample prep within an hour. I'll be flying through it a little bit, but you have all the notes, and if anybody has any questions, they can contact me with that. All right, so let's reconvene at the top of the hour. All right, thank you. The questions that we should recommend are artifact-free, but the sub-question we should ask ourselves is, does the analysis? And the answer is so damaged, then we're good to go. So strategies for FIB-SEM or SEM specimen preparation is really to take our start from our 2D sample prep and mill the other side of the sample such that we're left with about 100 to 200 nanometers thick sample. The other strategy is to start with this and continue to make it thinner such that we just cut through the sample so that we're looking at very, very thin material. While we're doing that, cleaning that up using lower and lower energy ions, which I'll talk to you about later. So the advantage is that this is really very quick. Somewhere around the order of 30 minutes to 4 hours, depending upon the sample type, what the sputter yield is of that material, and also the sample size. It's reproducible, better than 90% success rates. It's site-specific to 20 nanometers or even less. You can add automation for throughput. There's little or no specimen preparation needed for lift-up types, and it works really well for multi-phases and interfaces. All right. So the type of sample prep that we're going to be talking about is also perfectly applicable for atom probes, SIMs, UDSC, AJ, video construction, etc. All right. So getting back to this slide, basically the same type of thing. We're going to be sequentially milling through our different layers. We can also make plan view samples, which I'll talk about a little bit later. So remember, we can make our samples of just the tomatoes, in our Italian hero if we want to. Okay. Note also you can mill, you can fit parallel to interfaces as well. Remember that the slowest, the rate limiting step is the slowest sputter rate material. All right, so what we're going to talk about first is conventional or H4 pre-thin or cleaving, direct mounting. These are basically different ways to FIB mill a sample that is already pre-mounted on a TEM grid or somehow mounted on a TEM grid. Okay? And this can be done with gallium or xenon or basically any ion that you have. Then we're going to talk about in-situ lift-out, ex-situ lift-out, and some new methods that I've been working on. I'm going to show you some tricks and applications along the way. Specifically refer to TEM prep with xenon plasma FIB and low energy polishing. Okay, so again, comes back to this. You want to definitely protect your layers of interest. So if you've got something that's right up against the surface of your sample, don't even turn on the FIB until you've protected it, either with electron beam deposition, some sputter coating, Sharpie, or conductive foam, or some other way. All right. So conventional or H4 methods are so named because the resulting sample looks like the letter H, as you'll see. And this basically consists of getting a sample, by mechanical polishing or direct deposition of the sample on a 3 millimeter grid or half grid, and then starting to FIB mill on it. And we use the same type of techniques that I showed you earlier with 2D SEM. We use a large beam current to remove lots of material, smaller beam current, smaller diameter to start to polish it, and the lowest beam currents for the final polishing. And you want to tilt into the beam as needed. So it might be 1 degree, it might be 10 degrees, depending upon the sample that you're FIB milling, depending upon how that sample behaves and sputters, or redeposits, I should say, due to the V-shaping. Okay, so the pre-thin sample, the H-bar sample, is basically just that. So again, the resulting sample looks like the letter H. This was done in the mid-90s very routinely. This is just like a 2 metal layer sample structure. But with 30 kV gallium FIB is often just perfect enough to do just do some very simple Fourier analysis, identify different phases. You can see bright field TEM material contrast very easily. And note again that this was done on basically a 50 nanometer resolution glass column FIB. So you can make these samples pretty easily. Note these curtaining artifacts that you see here, the striations that occur due to different materials being patterned in different ways. Some of that is hard to get rid of, but I'll show you some examples of how to do that. Okay, so again, using the H-bar technique, but limiting, making the mechanically polishing the sample to smallest dimension possible prior to FIB milling to just save FIB milling time. So this is combining a tripod polisher plus the FIB. Less FIB time is needed. So that the starting thickness is just thinner. Okay. So here you see you can mount this in cross section and FIB mill a sample, or you can just by mechanically polishing the sample at 90 degrees, you can make plan view samples. And the advantage to this now is, say this slotted half grid, you've got 2 millimeters of open area. So now you've got 2 millimeters of material where you can FIB mill multiple windows across here. So it's advantageous in this way that you can make multiple samples up and down here. Similarly, if you have a plan view prepared sample, that is a sample that's just polished at 90 degrees with respect to this sample, I can then make FIB windows of, let's say, this is the bread, this is the tomatoes, this is the cup hole, etc. You can make FIB samples of different plan view regions throughout the one sample. So really advantageous to do it this way, and you really limit FIB time. Okay, so this is shown in the Infinite FIB book. So this is your cross section and your bright field TEM image. This is the plan view, multiple windows here, and this is an example of a plan view section. Okay. So again, the idea here is you're FIB milling on either side of the region of interest, leaving behind a thin sample. All right. Combining smalling and cleaving for FIB is also another way to just get the sample thin enough so that you can put it in a FIB to directly FIB mill on the sample. So with cleaving, you basically are left with a point at the end of the sample such that the thin area or the area at the end of the point is really electron transparent. By incorporating the FIB on top of it, you can make a FIB section. So there's a low snug bright field TEM image, and you can see very easily where the FIB section is being prepared to look at these thin layers. Shadow technique is another method. So this group basically just use the sample itself. They just use the substrate itself as basically a mask to FIB mill a thin section. So it's hard to see what's going on here, but the idea was to FIB mill from the back side of the substrate, leaving behind thin section so that the thin layer here was not touched by the FIB. Fold-out method, another way to make samples without FIB lift out. So sample was thin, cut into a 3mm disc, thin some more and angled, and then the FIB was used to shrunk out this little wedge-shaped sample. And then the FIB was used to cut perpendicular to this, so we cut 2 lines so that the sample fell over, and then continue to FIB mill in this direction so that you can put the electron beam through the thin area there. And you can see it. Again, these are ways to make the sample or FIB mill samples without lift-out. This is something I did with a graduate student at Georgia Tech a few years back. I was looking at carbon nanotube embedded carbon fibers. And first we did a longitudinal section by just gluing these fibers to these half grids. If you do this, the one thing that you definitely want to do before you FIB-SEM the sample is to FIB cut the sample through. And this will release any stress in these fibers. Okay, and this is really important because once the sample starts to get really thin with the FIB, you don't want to put any stress on this. So you can see here that in cutting the sample free, the stress release actually caused the sample to move, the ends to move several microns. And so if the final thin sample was just holding this together, that would put a lot of stress onto the thin sample and probably break the sample. It turned out that the transverse cross-sections were a lot more useful to look at. So I actually had the grad student glue these small pieces of fiber perpendicular to the original grid. I'll show you a better way to do this, but this was done basically with hand and tweezers using a stereoscope. And then basically then you just start to FIB mill from both ends until you're left with an electron transparent specimen. And I'll show you later when I talk about low energy polishing, I'll describe these different methods in detail. But just finishing with 5 kV gallium, we have to look down these carbon nanotube pores pretty nicely. Okay. Cryo-FIB TEM is possible. People are doing it more these days. It is non-trivial. Takes a lot of time, and you have to be really careful with all the cryo transfer steps. So you have to get a cryo sample into the FIB, do the FIB milling, and then cryo transfer it into a TEM holder and into a TEM. But nevertheless, it is possible to FIB mill on a cryo sample and do this work. Okay, so I mentioned earlier that a better way to manipulate samples is to, you can do it by hand, but a much easier way is to use ex situ micromanipulation, which I'll talk about in a little bit. But this is a way that you can manipulate small particles, fibers, particulates, thin films, particles to grids prior to FIB milling. So this is actually a longitudinal and a transverse cross-section of small fibers. And even for carbon nanotubes, obviously you're not going to FIB mill carbon nanotubes, but it's just a way to easily manipulate samples. And if you want to see those examples, you can look at my YouTube page here for lots of examples here. Okay, the one thing that I talk about when I do this lecture and talk about FIB-TEM sample prep is never, ever, ever, never, ever, never, never, ever. You don't want to FIB image your final TEM specimen using your high energy ions or ions in general. Why? Because as I showed with the simulations earlier, you can induce defects and you can get ion implantation just by imaging this sample. So once it's finished, you don't want to image your sample, and I'm going to show you some work by this group, which illustrates just that in a little bit. Okay. So in situ lift out is a way to basically get a site-specific sample, FIB milled, lift it out inside of the FIB, and then final FIB prepared. Once you get this chunk of material on a grid, then the rest of the FIB specimen prep is just like the H-bar technique. Okay. Key here is that final FIB milling is performed after the lift out to the grid. All right. So the way to do this is to, there's a bunch of different ways to do this. One of the ways to do this is to totally FIB mill a sample. 3, you insert a probe that's mounted either inside or on the chamber of your microscope. To get it to attach to the sample, you need to use platinum deposition or carbon deposition or tungsten deposition or whatever deposition you have. People call this welding. I don't like to call it welding because you're not welding. You're essentially just attaching the needle to the sample using your ion-assisted CVD process. Okay. Then you move your sample to the grid, and then you use your platinum deposition again, or whatever FIB deposition you're going to use to attach the sample to the grid. And then you FIB mill the probe away, and then you're left with this freestanding chunk of material now that you can subsequently FIB mill the way you would do any other H-bar type of technique. So this procedure itself can take several minutes to several hours, depending upon your level of expertise. Here's an example of why lift out in general is so useful. You can put in a chunk of material. This is cold worked aluminum. So without having to cut this up or destroy the fracture surface, you can just drive out to any location at the end of the tip. This is out here. Make a sample, pop it in the TEM, and now you've got your cold work structure that you can analyze and texture structure. Okay. You can also apply this to FIB embedded tissue for TEM tomography, not a problem. Lift it out the same way, make your TEM sample, and you can do tomography on this sample. Okay, to do plan view work, you have to somehow get your plane of interest parallel to your grid so that you can subsequently FIB mill then parallel to the grid as well. So in this case, the carrier or the grid has been put inside of the FIB and tilted at 90 degrees compared to the normal orientation. And so here, lifted out sort of a chunk of material, FIB milled a chunk of material, and then so attach the needle to the sample using the deposition capabilities. Attach this sample to the carrier with the carrier tilted over 90 degrees. There's your deposition. You've removed the probe away. And now you have to flip this up. So there are some stages that can do this inside of the FIB. If you don't have a special stage or substage, you have to break vacuum, flip the carrier or grid then upright so that you can FIB mill at any plane now parallel to that original surface. All right. This Hitachi group has shown that you can, after doing this plan view section, you can then cross-section a plan view of the same area. So after you FIB mill and do your TEM analysis, you can put it back in the FIB, attach the probe to the sample and cut it free, attach it to a substrate like silicon, and then cross-section the same area that you just looked at in plan view, and throw that in the TEM, and they've shown that you can actually do this 10 more times. You can do a cross-section of the plan view, and you can do another cross-section of the cross-section of the plan view. So pretty cool stuff. Okay, so the way you can reduce curtaining is with tilting, and this was first introduced by Mike Canute. Again, this is shown in the FIB book. So you can do this inside of your FIB. In some cases, unless you've got a special rocking stage, when you rotate and tilt, you won't be able to see what you're doing with the FEM. And so some people have incorporated these special rocking stages. I believe Hitachi, I believe Tuscan have these special substages, these rocking stages, that when you tilt and FIB mill from different directions to remove the curtaining, you can still see what you're doing with the FEM. Okay, another way to reduce curtaining is to FIB mill from the back side. So one way to do this, and this is something we did years ago, was to mount the grid upside down into the FIB. So when you do the lift out, then if this is your silicon substrate and you've got metal layers up here, the sample is lifted out in the same way. But then you have to and attach it to the grid. But then you break vacuum, flip the grid over, and now you can FIB mill from the back side. And this was work that we did, which subsequently gave to Molly McCartney at ASU to do some electron on. So we FIB mill this from the back side, and you can see now that there's no curtain artifacts in the silicon. Okay, another way to do this requires multiple steps inside of your FIB-SEM, and this requires multiple releases and tilting of the grid. So here's the lift out. The grid is perpendicular to the sample. Then you can flip the grid, grab it again, flip it over, and then you can eventually get the sample upside down relative to the grid by cut, release, cut, release, cut, release. There's another way that you can do it now with probes that rotate, but you have to know at what angles to connect things at because you're dealing with compound angles with probes inside of the FIB. And I'm going to show you a third way once we get to exit to lift out. There's another instrument or substage that's available. This is called X2 milling, and by just rotating the sample 180 degrees provides this cam rotation of 45 degrees so that you can cut two different sides of the sample at two different angles, resulting in a thin area that's supported by a thicker area of the sample. Kind of a neat thing, but I think this is only available on those tools. Cryo in situ lift out is also possible by doing lift out with a cold chip. Again, this is non-trivial. This requires, of course, that the lift out probe chip be cold. So all this is under liquid nitrogen conditions on a liquid nitrogen stage inside of the FIB. Final thinning, and then you have to do the cryo transfer all underneath liquid nitrogen to get it into the CEM. But it is definitely possible, although it is very time consuming. Okay, atom probe techniques basically consist of lifting out a big sample, long sample, I should say, taking the end of the sample, putting it on this microchip or just a TEM grid itself, cutting it, attaching it, and then cutting it free, and then you've got still all this length of sample and then some to go and put multiple samples on multiple tips, and then you annular milling now to subsequently get the sample thinner and thinner. And as you get it thinner and thinner, then you also have to use your low energy polishing, again, which I'll describe later. But this is an example from the technical note showing a bit of sample lifted out onto microchip, and then the process of going thinner and thinner. This is higher magnification, showing the tip that's ready, a little bit of cotton still left on the tip. Okay. And this is work that I did a while ago showing that using make these pillows just from planar samples, of course, as well, just milling out a certain piece of the planar sample. And then, of course, you can take these, sorry, let me back up again. By virtue of the size of these atom probe tips, they also happen to be electron transparent. And so it's often useful and in some cases necessary to take a TEM image of the sample before you do the atom probe work so that you can correlate your atom probe results to the structure that you see in your TEM results. The other thing that you can do with these pillar-shaped samples is on-axis tomography. And again, this is work that I did with the group at Sandia. So you can put these pillar-shaped samples at the end on a special holder. This is a Fishion holder that rotates the sample around on axis 360 degrees. You know, you have to do 180, of course. And this is looking at these particles, nanoparticles, in a kit. And so you can do 3D reconstruction and tomography, in this case using EDS. Okay, so now to exit to lift out. I'm sort of going backwards in time because this was historically the first lift out technique developed. Again, all the advantages of in-situ lift out except for you're doing this outside of the FIB-SEM. There's no prior sample preparation. You completely FIB mill the specimen on all sides. You manipulate the specimen outside of the FIB. And if you're using this for TEM sample prep, you want to do also your final thinning inside of the trench, and then you cut the sample with tab straight, and you'll say this. Then you can mount the sample onto a carbon-coated TEM grid or some other holders as well. And I'll show you various examples of this. So, and in fact, if you go to the early literature, you'll just see reference to lift out. You won't see reference to exit to lift out because there wasn't another technique. So, but this is very similar to what you would do with any 2D sample prep or even the start of in-situ lift out. So there's your sample, your deposition layer, trench in the front, trench in the back. Continue to make it thinner. You undercut the sample. In this case, there's only one little tab free. I like to do 2 tabs now. But after you tilt the sample back down, you thin either a portion or the entire sample to electron transparency. And then you cut the sample free such that you have a completely freestanding sample inside of the trench. And then you pull that out of the instrument. And now back in the day, we did this on sort of a do-it-yourself cobbled system. And then a company started to buy systems. And now, full disclosure, this is what I do now as part of my business, is to actually provide these systems. But this is very fast and easy to do. So again, you can go to my YouTube page to look at videos. But this is start to finish a lift out sample in basically just a minute and a half. So you can think about being able to lift out 20 samples or more per hour. So it's really fast. Back in the day, people asked us, how does this work? Is this electrostatic forces? And we kind of just shook our heads and said, okay, sure. But most recently, I went back and actually looked at diffusion forces. And it turns out that it's van der Waals forces in play. So here, if we plot on a log scale of the diffusion forces as a function of fixed specimen length, turns out that the van der Waals forces are actually the strongest, the capillary are somewhat weaker, and the electrostatic forces are actually the weakest of all diffusion forces. So if you look at this, this predicts that you can actually manipulate samples on the order of a millimeter or longer. It's interesting, if you take a look at the Van der Waals force equation, there's two things that we know. One, of course, is that the adhesion force is proportional to the surface area, so the more surface area you have available, the greater the Van der Waals force is. And also, this Haymaker constant, H here, is a material constant, and this varies 2 orders of magnitude over the periodic table. So if you take a look at this log-log plot and vary at 2 orders of magnitude, you've still got 10, 12, or more orders of magnitude larger than the force of gravity acting on these small big samples. So this is why it works, and this is why it works very well and reproducible. And in fact, what you want to do is totally avoid electrostatic forces. And the way you can do that is to just metalize the glass tip. You can do that by either metal coating the glass tip, or by using the Sharpie ink set again, as we learned before. So just use a permanent marker ink and just coat the tip, and this totally avoids electrostatic forces increasing the Van der Waals forces. So just one other question, people always ask me, why don't we just use a tungsten metal tip? And the answer is, if anybody has accidentally smashed a tungsten probe tip inside of their FIB when trying to do in-situ lift out, they know that the tip will curl up like a little elf shoe. So this will happen too, if you just touch the inside of the trench with the tip. So by using the glass probe, it's stiff, but will flex a little bit and without deforming. So that's why we use the glass probe and just metalize it if necessary. So we didn't know at the time when we made all these samples, from semiconductors, from metal powder particles, to ceramics, to polymers, to geological materials. We were concerned with being able to FIB metal these samples. What we also learned is that these Van der Waals forces actually work for all of this as well. Because of the reason I described earlier, because the Haymaker constant varies only a small amount relative to the Van der Waals forces. So someone asked, do you have to coat the entire needle? So the answer is, I don't know. I have tried it both ways. I think you can get away with just coating the tip. Yeah, I've tried. In this example, the entire tip is coated, because this is the part that sticks into the holder. But I think what I've been doing of late is just coating up to about here. So as long as the end of the glass, the tip itself is coated, I think we should be okay. So you can do plan view ex situ lift out, not a problem, by just positioning the sample into the FIB at 90 degrees and doing a plan view type of sample. Here's something that Richard Langsford did years ago by using ex situ lift out, just cutting a big trench, using it to manipulate the sample upright, putting it back in the FIB to lift out or to thin this sample, and then cutting it free and using the probe to place it on a carbon 13 grid. Richard Langsford also showed that you can lift out a sample and put it on a smaller grid opening sample, and then argon ion mill one side, and then flip it over and argon ion mill the other side to reduce 30 kV FIB damage. And as I mentioned, you can manipulate a lot of things to grids to get them ready for FIB sample prep, to do then the so-called H-bar type sample prep. So to facilitate this, you might want to use glue. So this is the probe going into M-bond glue. And now you can use a little blob of glue on the end of the tip as a little paintbrush. So here, we just paint the inside of a slotted grid. And now you can go back and grab a particle. Now, in this case, you don't have to worry about changing out the probe per se, so it's okay to have this probe still have a little bit of glue on it, because you're going to subsequently signal it anyway. Okay, so once you've got particles on the grid, then you can go ahead and straight away signal it, so it makes it much easier and much less dead time. So there's your glue, there's your particle on the glue, there's your platinum, there's a FIB image of the sample, still about a micron thick, and then there's your subsequent ion going there, just this image. Okay, this technique turns out to be actually perfect for doing in-situ TEM, where it's required to get an electron transparent specimen on these various MEMS devices that are made by various vendors, such as Protochips, SEM Solutions, etc. So for these in-situ MEMS devices, you need to get an electron transparent specimen onto the grid, and it turns out this is the perfect way to do it without FIB damaging your sample via FIB imaging via in-situ with that. And here's some additional work by the group at Drexel showing ex-situ lift out of these samples, subsequently put back in the FEM to tack down the samples using E-beam deposited platinum, not ion beam platinum, because you don't want to ion damage your samples. And this just prevents drift during the heating experiment. And then this was done in an environmental TEM. So you've got an oxidizing environment at heat, and you can see then oxidation at the green line. So as I said before, never, ever, 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 never FIB image of SEM or anaprobe specimen using high-energy ions. And this is an example showing what can happen if you do this in-situ experimentation using in-situ lift-out versus ex-situ lift-out. Because by virtue of doing in-situ lift-out, you inevitably have to turn on the ion beam at some point to be able to see what you're doing to get the sample down to the MEMS device, whereas this is not the case with ex-situ lift-out. So what this shows you is in-situ lift-out after FIB imaging gives you similar results to ex-situ lift-out after the annealing experiment. And so without even doing the annealing experiment, you get ion implantation damage and ion basically interdiffusion due to the ion implantation that looks like what your heating experiment looks like. So you can also lift out thick samples, so very easily polish a sample up to 1 or 2 microns thick. And that was real time, by the way, so just in a few seconds you can get a thick sample out and quite specifically do, for example, SIMS, XPS, OJ, etc. So it's a really fast and easy way to lift out any sample that you want to analyze without having to get it electron transparent. And Joe Michael, again, uses this technique routinely for lifting out thicker samples to do EBSC, top-down SEM EBS. And this way you can optimize your collection angles also, so that you can do, for example, SEM EBS, top-down perpendicular to interfaces, or I should say parallel to interfaces, rather than at some tilt of the electron beam at some tilt to your sample surface. You can lift out bigger samples, so 40 micron long sample, for example, so you can do this using your plasma FIB samples, not a problem. You can take advantage of your automation that might be available on your vendor's instrument, whether it be AutoTem or AutoSlicer or whatever some other vendor comes up with It's a way to make these multiple samples very quickly. And again, you can, back in the late 90s, there's recent technologies that I was working with, they were making 1,000 samples a year. And today it's not unheard of to make thousands of samples in a month or even a week. Okay, so advantages to ex situ lift out: site specific, little or no sample prep, really easy to master, it's fast, reproducible, saves good time, etc. What I want to end up with is talk about just a different technique using ex situ lift out without the use or need for a carbon film. And this just gives you flexibility. You can lift out an electron transparent specimen or a thicker specimen directly to a grid. The grid itself forms the support. In this case, you can manipulate it easily into a backside configuration, do your final FIB milling, and you get no certain artifacts. So I want to show you how this is done. And what I want to emphasize is that this is not what I refer to as claymation. So that's a real clock in real time, just sped up to avoid the boring parts. But the point is, there's the lift out. The idea is to rotate the sample, rotate the probe so that the sample is on top of the probe. Then you can use the grid itself to manipulate the sample and just orient the sample with respect to the probe in a preferred manner. So you can spin it around the probe, you can center it on the probe, and then you just slide the probe through the open slot, allowing the specimen to come to rest on the grid. And so that was just over about 2.5 minutes. So pretty easy to do. You can FIB mill the sample after the sample is already on the grid without any additional deposition, either with FIB or with an argon ion mill, such as a nano mill or pico mill. So you can do your low energy polishing as well. You can use it for transition to Cucci diffraction or EDS or whatever, using different geometries. You can also use vacuum and pull vacuum through a hollow probe, and this double hollow probe to optimize collection angles. Something that did recently, again with the group at San Diego, this is a double hollow probe. Doing plan view analysis, they lifted it out, flipped the sample over 180 degrees, and just placed the probe through the slot, allowing the sample to come to rest on the slot. This only took a couple of minutes to do. And then you can subsequently FIB mill to do your plan view analysis. Again, making larger samples for Xenon plasma FIB is just as easy to do. And this was the work that I showed early on. A large sample lifted out, placed on the grid, in this case using N-bond glue as well, but there's your EBSD and stem analysis. And you can also optimize the thermal forces by making larger flat surfaces. Okay, so just some generic stuff, how to deal with specimen warping. A couple of things you can do is you can relieve the stress with a FIB cutter too. You can just make smaller windows. You don't have to thin as big as material. Here's an example using ex situ lift out by just FIB milling this little arrowhead. And this little arrowhead allows the sample to move slightly but still staying sort of upright, if you will. And then the sample is just cut free over here and then manipulated to ex situ lift out. Okay, now let's just finish up by talking about low energy polishing. This is really important when we want to reduce big damage for high resolution Ion-SPEM or even for analytical tomography. So we know that if we take, for example, silicon and use 30 kV gallium on each side, this is going to result in about 22 nanometers of sidewall damage per side. So if we have a 100 nanometer thick sample, that means only the center 56 nanometers or so is totally pristine. Or I should say, not necessarily pristine, but not amorphous, okay? If we continue to get this sample thinner and thinner, obviously we're going to get to a point where the entire sample is just amorphous damage. So what I like to do then is to start with a thicker sample. Let me go back first and talk about what's the impetus then for doing low energy polishing. We can reduce the ion energy, which reduces the ion range, which also reduces the damage depth. So this is one of the graphs I showed earlier on, which shows that all these different ions, we take a look at the ion range, they all converge down to the really, really small value of about a nanometer or so, if you can get the ion energy low enough, okay? Helium is sort of this outlier. We're not going to talk about helium per se. And this graph here is perfectly shown by the experimental work here. So we look at this experimental work that shows damage layer thickness for xenon and gallium. At a beam energy of 30 kV, we see a huge difference, 41% difference between the depth of damage of xenon with respect to gallium. Of course, xenon is a higher mass, heavier mass, so it's going to produce less damage based on what we know from our ion-solid interactions. As we go to 5 kV, the difference is less, and as we go to 2 kV, the difference is even less. And this is shown here by this graph, right? So as we go to lower and lower energy, the difference between ions becomes less, or becomes insignificant. And so my story would be, you know, it doesn't really matter what ion you use per se, as long as you can get this ion energy down really, really low. Now, you might want a particular ion over another because it may react with your sample, but that's another story. Okay? So, the other thing, again, I showed you this graph earlier. This actually works to our favor when we do low energy policy, is we take a look at our theory and we take a look at our ion range as a function of ion energy and incident angle. We see that the ion range varies a bit at 30 kV, but if we go to 5 kV or 1 kV gallium, we see that this is very flat. So the ion range isn't changing all that much as a function of ion energy at these low energies at incident angles. So what this means is that what's going to do or work for us at low energy is just the ion energy. And we don't have to worry so much about what angle that we hit our sample at, okay? So, and of course, whatever we do to side 1, we have to do to side 2. So this means that we can work with 10 degrees or so if we need to. If we need to be able to see, just see where that sample is, we can go to greater angles relative to the sample surface, and tilt and be able to see where we can put our ions. So this is just the experimental work that we did years ago that shows that you can increase or decrease the sidewall damage by going to low energy. This is no surprise these days. So the idea is, and what I like to do then, is to start with the sample thick, generally about 200 nanometers. That will just give you more sample surface or pristine sample to work with in the center of your sample. Get it nice and thin using 5 kV, and then do an endpoint. And this reduces the sidewall damage to only a couple of nanometers on side, and then do your final polishing at 2 kV or less with either the gallium, xenon, or your offline or then ion. Okay. And there, of course, is then again work we did years ago showing that you can go to 2 kV finish and definitely improve the image quality. Okay, so this was the work I showed you earlier with this carbon nanotube carbon structures. In this case, I only finished with 5 kV because this is all that I had on this older FIB. But what I like to do is use my 30 kV to endpoint and basically get it thin enough to make it core electron transparent. And this thickness is going to change for different materials, of course. And then at this point, I've switched to 5 kV FIB. And then basically what I'm doing is, what you see here is the contrast goes from dark to bright in the SEM image. And the reason why it goes bright is because you're getting secondary electrons off the front surface as well as the back surface. And then you're going to start to get to a point where the contrast goes dark again. When the contrast goes dark again, now you're mass limited. And so this area is getting really thin. And in fact, I've gotten to the point where I've actually punched a little hole through that. So this area right up against that hole is probably only about 20 or 30 nanometers. And now from this, I can stop here or I can switch to 2 kV or lower if I want to, just to kind of hit each side just 30 seconds or so. Okay? So these are some examples working with collaboratives that I did years ago. This was working with Cornell, looking at STEM of high temperature superconductor metal insulating hoop plates. Very easy to see these different layers. This, of course, is very useful for doing EBSD analysis as well, which is also surface sensitive. So it improves the low energy signal, improves your hit rate of your EBSD analysis. And it turns out that 5 kV is absolutely necessary for anaprobe analysis, and 2 kV is even better. So you can't do anaprobe analysis with 30 kV, you just get too much implantation across the tip. Of course, as I showed earlier, low energy milling with argon works just as well. As long as you get the energy of the ions low enough, it really doesn't matter what ion you use per se. Can you do TEM prep with helium ions? I don't think so. Someone can convince me otherwise. But the problem is because you've got so much electronic stopping, and then you get the nuclear stopping well below, you just get too much damage before you start to get sputtering. Can you do TEM prep with neon ions? I think probably, yes. But I'd like to see the neon energy come down somewhat, because right now 10 kV neon is similar in damage to 30 kV neon. So because of the graph I showed you earlier, the neon energy needs to come down somewhat to make it useful. And just, again, something that I just introduced of late is this 3D printed samples. And with these 3D printed samples called practices, you can actually practice your in situ or ex situ with that sample prep. So it's a way to train new users on manipulating samples without having to use extensive FIB time to actually make the initial samples, because it's got being all 3D printed. And you can then just cut them free for ex situ lift out or do the in situ lift out as you would with a conventional analysis. Okay, so perfect timing. To sum up, you need little or no specimen preparation for FIB prep. It's site specific, it can be very fast. You can make samples for basically virtually any materials or any types of geometries. And you can produce high resolution quality specimens with sub-instrument resolution using low energy techniques. So with that, I'd be happy to answer any additional questions. We still got almost everybody almost everybody made it through the full 4 hours. So if anybody has any questions, please type them in. I'll hang out for another minute or so. Oh, this is the question. How do you clean up FIB curtaining? FIB curtaining, you can do that one of two ways. You can you're going to have to mill from different directions, or if it's a semiconductor sample, you can mill from the backside. So let me go back to, let's see if I can find it. So yeah, okay. So with FIB curtaining, you're going to have to, so if you have the Intro to FIB book, you can go to page 162, and my student shows you how you can do that on a FIB. Well, basically, it consists of coming in to the sample surface at different tilts with the ion beam. So conventionally, you would be FIB milling parallel to these lines. So it's a way to rotate and tilt such that you come in at 2 different angles. Okay? Or if it's a semiconductor sample like this, you can mount the sample upside down in the so-called backside configuration and mill from the substrate side. And that, then you don't get curtaining in the substrate, but of course you'll get curtaining anything in the metal layers. But that usually is not a concern. So another question was, any good resources for preparation of nanoparticles via FIB-based approaches for atom probe analysis? So what I would recommend to do is something like, where is it? So depending upon how big the particles are, so I would use ex situ lift out just because I wouldn't want to ion image my nanoparticles. Let me find that. Let's see, so what I would do is that, oh, there it is, that blue technique. So I would do something like this, where you can dip a little N-bond maybe into onto the micropillar, maybe directly, depending upon how big the samples are, either onto the micropillar array or onto the grid itself. And then you can put the nanoparticles on top of that. And yeah, see if the glue is strong enough. If the nanoparticles are already, then of course you would use a clean thread kit to mount them on there. If the nanoparticles are still too thick to be directly atom probed, then of course you can subsequently FIB mill them to the correct size. But that's what I would do. If you want to try it, you can contact me afterwards, and I'll be happy to try it for you if you don't have an ex situ with that station. So, any other questions? See some people. Thank you for attending. Really appreciate it. Again, if you have any questions offline, please don't hesitate to send me an email, shoot me an email, and I'll be happy to try to suggest something for you. All right. Wow, we finished right on time. That was very fortuitous. Any other questions? No, good. Okay. Have a great, great rest of the day, everybody. Take care, and thanks again, and be on the lookout for more ABS presentations. All right. Thanks a lot.